Thanks, everybody. Thanks for having me. Here is good? Awesome. So today, we're going to talk about this topic, data cleaning. And I know that we have two slots, an hour and a half each. So the first slot is going to be more of a survey, if you like, or background work about what happened in the area. And then I have a surprise for you about how important this work at the end of the first part. That will make you want to listen to the second part. So that's the plan today. Let's make this interactive because otherwise it's going to be a dump of a lot of techniques. So I'm depending on you to interrupt me and say what the heck that means and you're wrong. These kind of things I like. Sounds good? Okay. So I'll tell you why. How many people know about data cleaning or worked on data cleaning a little bit?
What the heck that means?
I love it. Okay, good. So it's a mixed crowd. A few years back, there will be fewer hands up. So I'm actually happy that so many people working on this. So why this is a notorious problem? You'll see throughout the talk, it's a mix of practical industrial experience with some academic work. And I have one or two legs there and one leg here. So hopefully we get what does it mean and why the interaction between industry and academia has been very awkward marriage for this problem. So it's suffice to say that the percentage of our papers in academia that's actually in industry is less than 0.1% in this topic. Very few papers have made it to any commercial product. Not because the papers are dumb. It's because the gap, the evolution gap between industry and academia is really strong and big. So one of the reasons is trying to understand what is the pipeline of big data, data science. Everybody is familiar with this, which is what we use usually to represent sources and acquisition. In industry, it's called the ingest box of a stack. So if you're in industry, you'll find some engineers working on the ingest box. And that's their definition of how to acquire data in. And this is where you buy a lot of iron and you get into data center business and virtual private clouds and PVCs and what have you. And people like this because you buy iron, you have a big data stack. And then start people to dump this data on it as much as possible. So now we're extremely fast. And if you heard about things like Kafka and what have you, building pipelines to get data in becomes now super easy. So now they created a problem because this data comes a lot easier. Independently, there is other set of people who are very interested in creating really pretty pictures at the end. So Tableaus and Domos and all of these new startup, what now used to be startups are now big giants, were focused on analytics. So assuming the data is clean and you made some magic to go from here to there, how to build the analytics and how to build visual interfaces and interact with the data visually. And these are billion-dollar industry, and this is a billion-dollar industry. Everything in between is really bad. So the biggest task were manual labeling and fixing efforts and stuff like that. It used to be, these are old statistics, but this is really 60 to 70% of data scientist time. We're talking about in New York, a data scientist starting salary is close to 200 to 300K. It's a lot of money. They're usually smart kids from, I just lost my undergrad. I told him to stay for PhD, and we are in camera, so I cannot tell you what exactly he did to me, but he had a 300K offer compared to the awesome 30K offer that I gave him. Did not work very well. And in this 300K offer, what he would really do in the first few months, he would be eyeballing Excel sheets, moving things around to kind of massage the data that can he shove it to the analytics and TensorFlow and PyTorch. It has to look like a data frame. It has to look like an Excel sheet that I can push to analytics. So that's 60, 70% of the data. Massive labor work. Independently, also, if you read about machine learning and the new craze in machine learning, there is a lot of emphasis in building robust models. If you heard about this robust optimization and why the theoreticians are getting into machine learning like crazy, because they understand that robust optimization is one of the most important things in machine learning. The whole idea there is, can I learn from noisy labels? Can I build machines and classifiers that can take noisy data, noisy training data, and still can come up with a sensible model? And indeed, we do really well in that domain when the data has enough redundancy. I mean, you're going to understand this more towards the end of this lecture and next lecture. What does it redundancy mean, and why it's a really bad thing in databases, but it's an awesome thing for machine learning. In between, tons of companies have been created. This is in between now in the last few years, 6 years or so. This is more than $30 billion industry. And these people do nothing but shoving data from here to these pipelines. And you can see there are things that some of you might be familiar with, like Informatica, Alteryx, they're all billions of dollars of revenue. But there are also up and coming. Tamer is a company that I'm involved with since 2011. I'm going to tell you about, and Trifacta out of Berkeley, and there are old people as well, like IBM and SAP, and they're getting into this business very quickly. So I'd like to understand why this business is booming, and what did we have to do to contribute to that business, and why we still have massive opportunity for impact beyond the publishing papers in data cleaning. So what does it do? What does it really mean? The meaning of data cleaning, people don't care really what's your definition. They just want to extract value from data that looks like a can of garbage into something a little bit tidy and understandable. And everybody see it as the hurdle to data science. So if you heard all of these Forbes reports and so on, they recognize data cleaning now as a problem, as an important problem, and they're willing to throw money and resources in it. So what do we mean? It's a bunch of exercises that remove errors, filling missing values. Some of you might be familiar with some of these sub-problems, like missing value imputation, transformations, and program synthesis, mapping and aligning columns, and I'm going to get into schema mapping and matching and information exchange, remove duplicate record, fixing integrity constraints. All of this is what we call data cleaning, that kind of bag of tricks that we're going to use. But most importantly, today, I'd like to convince you that there are actually at least two classes that are extremely distinct from each other, and we should not put them under the same pot. The first class or pot, I would like to call it data unification. And I know it's cheesy, but that's kind of what Gartner is calling it right now. So it's important to know that that's what people talk about. And this is what for us means data integration. So all the problems in data integration is a combinatorial problem, because the problem in data integration mainly, other than the semantics, is engineering problem. Because if you think about it, the classification problem in data integration is a trivial task. Are two things the same or not? Is this column, is that record, is that record? And then you do your actual mapping. So the classification is not that hard. But you cannot run the classification on all the pairs of things. So it requires heavy engineering. So let's try to, with a grain of salt, we'll call this easy machine learning hard engineering. And there is a data repair problem where the engineering is not very well understood, but the machine learning problem is extremely hard. I need to look at a cell, like your address, your salary, and I'd like to come up with the most probable value that should reside in this bad cell. So it's not an integration problem. It's an actually hard problem, either classification or regression. It's kind of a hardcore machine learning, and you need to invest. What are the features? What are your representation layer? Are you going to do it this way or that way, where you get training data? And sometimes it's the engineering is actually trivial. It's linear. It's just, and we're going to get into those. So if you're not familiar with these, I'm going to give you just flash slides what the main problems are. An example of a unification problem is something that is dear to our heart, schema mapping, because we have lots of papers in the database community on schema mapping. And it's aligning, it's a bunch of exercises. It starts usually by aligning columns and understanding that this column here is this column there, and some sort of combination between these things, like this PN is part number. And then usually followed by other exercises. For example, how to go from one instance under schema S into another instance under a different schema T, under some mapping constraints, or usually highly declarative language to recognize the relationship between S and T. And there we contributed a lot. There is a massive literature and very smart colleagues on information exchange to do this and study the hardness of this problem. That source to target generating dependencies and TGDs and EGDs, there is a lot of papers really. You'll be surprised that the most important topic that we focus in academia, which is this how to go from one to the other, is the least important topic in industry because they struggle with the first step. They're struggling with matching columns. That's for them is the hurdle, not to what well, after this, they hire people and do it manually. So we're going to recognize that. This is a picture that I found on the web, and I think Yanis, it's close to his heart at some point. And this was a screenshot from the Clio system at IBM long time ago. And this is how schema mapping visual exercises look. A semi-automatic way of saying this column is this column, and there is one-to-many relationship, and that generates higher level specs and so on. So the reality was why this didn't really take off, why you're not seeing Clio in the hands of every industry now, is the best working algorithm for schema mapping is to hire 10 people to do it. That's how Kayak works, how all of these meta searches work. They look at this and say, this is very cute, but I can hire 10 people and ask them in a month, map all of these, and they write scripts to do it. And that's true. It started to become important again when we started to have use cases in which we have hundreds of thousands of sources with different schema. Now you cannot hire 10 people again to do it. A concrete example from industry, and this is pharma, a pharmaceutical company. So what pharmaceutical company do, they do these essays and clinical studies all over the world, mostly third world country when there are less regulations. And there they get reports from people about what happened. And that report usually follow a schema made up by that local country. And comes to the headquarters every week, hundreds of thousands of these schemas that they need to be mapped together and put in a standard called CDISC to be able to publish and to do things. And there they suffer. So a big pharmaceutical company that we deal with in Tamer, for example, it takes them few weeks per case. So at the end of the year, they do like 50 cases or so, while automation can take them to 1,000. Imagine the acceleration that they can do in discovering drugs. Okay, so this is a good example. This is a more familiar problem to all of us, which is deduplication, record linkage. And if you think about it, it's the pivot of this other problem. Now I'm interested in if multiple records mean the same thing. So I'm not interested in mapping. It's one source. So there is no multiple sources. But I would like to know if these records are actually mentions of the same real-world entity. And this is a very, very famous problem since the Census Bureau in the States, when they started to ask people, and then the same person get asked by multiple agents, so they end up by duplicates. And in acquisition and in merger and acquisition, where you will get the data set from all your subsidiary, then your customer, Toyota, for example, might have all their data from all their customers in Europe, and you walked into Belgium and you registered under your short name or nickname, and you know, in Spain you're under your full name, and somebody asks for your passport name. So Toyota think they have 3 different customers, but actually one customer. And sometimes this is a disaster. For example, in one of the customers that we deal with for these, the reduction was like 50 or so. Like you were wrong by an order of 50. So it can be disasters. Let's go through dedupe. If I give you this table and I ask you to do dedupe, if you know this, you don't have to answer. But if you don't know this and you want a quiz, so you can wake up a little bit with me, what do you do? What is the first thing you do? Find duplicates in this table. Sorry? Thinking like a true database person. Yes. So let's assume that I don't have any functional dependency. Ignore that these columns make any sense. I mean, I want a more stupid answer.
Ordering them?
Okay, on something?
I don't know.
And if you order, I mean, why you're ordering them? You're on the right track. You want to do a comparison, right?
Column by column.
Other another ID.
On ID, column by column, and I do it. So all of you, you're probably thinking of how do I kind of compare things, right? And I'd like to compare things in smart way because I'm answering a question in front of 60 people. So I need to come up with a very good answer. But it's indeed all what you need to do is to do this. You're all right. I want a way in which I can compare every pair and I come up with a score of how matching they are. If we did it in a stupid way, we know it's kind of a nested loop and I get n-square comparisons. But I'm assuming that, we're going to think, oh, how do we do this without n-square comparison? But these numbers, where do you think these numbers coming from? What will be your suggestion to come up with these numbers? This is, think about it as a score of a match. The probability of two things are the same. Similarity metric. On what? Distance. So now you start to think of, oh, I actually need similarity functions. It looks like I can think of distance, and if it's numerical attribute, I can do absolute difference. If it's our strings, I need to look on my book, but probably get a Jacquard or edit distance or something. And either you need to trust one or you do them all and then combine them in some sort or shape. Okay? So that's good. After this, what is the problem with this picture? Like, let's assume we did this, and I'm going to come back to it again. What will be the problem? It's harder to see. The problem might be because we yes, sir?
Because even if we have these clusters, it's very hard to define what this entropy is. So we don't know what the actual value is. So we have to estimate.
Right. You're ahead of me. You're absolutely right. And I had a problem even before this because you assumed I'm going to go cluster, and I was trying to motivate you why I need even clustering. We shouldn't need clustering if this is a very faithful metric because it's going to put everything together. But you will discover that P1 and P2 is very similar. P2 and P5 are very similar, but P1 and P5 are not similar. And we know that, it cannot be true. Same as relationship is transitive. And the proxy that we're using here is not. So I needed clustering, which is exactly. So I'm going to do clustering algorithm first. What is the right clustering algorithm to use? K-means. And if you're, if you love clustering, clustering is fascinating. I have a good friend of mine in Waterloo, Shai bin David, who I always tease him that he wasted his life on clustering. He is the clustering god of the world. He knows every clustering technique, and it looks like it's not an easy subject because every clustering algorithm have a different objective function underneath. Like, I don't know, if you're like me, when I started to be introduced to cluster, I thought it's a taste thing. I like k-means, my friend like agglomerative clustering. It was a little bit deeper than this. I think it's, so you need to understand what is it that you're optimizing. So for example, k-means is very good if I know that there are k entities and you have a good starting guess and so on. But the closest to what we want to do is actually a version of correlation clustering. Because in correlation clustering is a way to kind of minimize disagreements of these labels, if you like, right? These guys are labelers that tell you P1 and P2 same, P1 and P5 not the same, P2 and P5 same, and so on. Let's assume that I did this. I would like a way to correlate, to cluster them together, minimizing how much I'm disagreeing with these binary labels. Very hard problem, and that's why we go to a more practical solutions like agglomerative clustering. The most used clustering technique there is hierarchical agglomerative clustering, like single linkage, something very greedy, and it works very well in practice. Let's assume that we clustered. Then we come to the problem that was mentioned. What is it that, like this is not represented in a table. It's useless in a table. I would like this. I would like to come up with a golden record for every cluster. And that's already a black magic already, because it depends on the semantics of these clusters. For example, if this was the height, you're probably okay with the average. You're assuming that people are not growing in your company, for example, more because they're all, so average is probably bad measurements. But if it's salary, you probably want to get the max because people get promoted. If it's an address, you might want to put them together in a multi-valued attributes and say, oh, because I want all your addresses, and I would like another table. So it's very domain dependent. So let's talk about this red number here, because that's the only machine learning piece in it. The rest are, I mean, if you like to call clustering machine learning, fine, but the rest is, the only part that I kind of need some probabilistic interpretation is this idea of a score. So you will be surprised how easy it is. I take the table, I generate a pair space. From each pair, these are examples, C1 and C2 are two examples. I start to generate a feature vector. Okay? This is all what I think distinguished. This is kind of Stone Age machine learning. This is the good old feature engineering business. And then I teach a classifier to know the difference between match and not match by showing this classifier a lot of examples. These things are the same, these things are not the same, these things are the same, these things are not the same. And hopefully that classifier will find the boundary, the decision boundary, and say, okay, if you show me a new pair, I can give you a match or not match, and hopefully with a score as well. So it seems that it's kind of a 101 high school machine learning, so it's good. So why this problem is hard? So before I tell you why the problem is hard, Tamer, this is a small example of Tamer backend architecture. And Tamer is 120 employees and $60 million in funding. So either we're really dumb or the problem is actually hard. I'd like to think we're not that dumb. So why a problem like this is very important, or why it requires all of this? Because just to do what I just told you, I need to come up from source data. I need a way to generate all the pairs. I need to materialize the pairs because I would like an incremental processing. I'd like tomorrow when you give me a pair, I don't do this again, right? So I need state that is indexable. So when you give me a new data set, I can poke what I know and I give you other pairs, no? And then I need to materialize a feature vector for the same also high availability. And then let's talk about this orange thing. This orange loop is it's an active learning loop. And one of the first papers that talk about active learning in this problem was Sunita Sarawagi paper in the 90s. Fantastic paper. It's actually one of the heavily used idea. And if you're not familiar with what active learning is, in a nutshell, it's a way to teach a bunch of dumb classifiers to agree together. And whenever they disagree, that's a good suggestion to ask the user to get more information. So I'm going to create here an ensemble of models, right? And these models, whenever they disagree, it's a good point to start making the differentiation between the two classes. So I'll start to buy some training data. I build initial set of classifiers. I pick some of my labeled pairs. And I see if they agree on it or not. If not, then this is a good suggestion to send back to the user. The user will label it, put it back in the training data. And you do this active learning loop. Is that thing? No. Yeah. This active learning loop, you keep doing it till you graduate these models. Okay? So they're not so dumb now because we got them initial data and then the hard cases as well. So they learn it. And then I start to label these pairs for real. And I put through clustering. And I materialize these clusters. This little box, which is called cluster validation, is also an interesting problem. Cluster validation is, if you think how people consume input, human in the loop kind of business, it makes zero sense to show people pairs. If I'd like to take your opinion, if I did right or wrong in a data duplication problem, I should show you the cluster. And I tell you, are these people the same or not? And in your head, you're going to do a lot of n squared. And you tell me, no. These guys are the same, but these guys are not. Right? So the input to clustering is actually an interesting problem. And how, from that high-level split and merge, you generate pair space label data, for example. So that's kind of a lot of engineering to build this pipeline, and it doesn't work as is. Can you tell me what is the biggest problem in this paper? In this, figure. It will never work as is. There is something here that will blow in your face. This guy. The n square. I shoved it under the rug very quickly when I'm talking to you. I generate the pairs, and then in pairs I go to the features. But think about like 200 million records in your data. What pairs you're going to generate? You're going to run out of computing power and space and lifetimes before you generate 200 million square space. So luckily, also our community had a lot of work in solving only this problem.
But,
Yes, sir.
The pairs, like, from my understanding, like to learn the model, we don't have to use all the pairs, do we?
No, but we want to apply the model eventually on something. So I can start by, right.
When you want to do the actual comparison, right?
Yeah, I actually want to apply the model. Yes, sir.
I see. And for
Sorry, you have to, yes.
yeah,
Go ahead.
Another question.
Yeah.
For the models, what would vary? Is it the algorithm or the features or both?
Here in this ensemble,
Yes.
in Sunita's paper, it was different parts of the space, so different pieces of training data, and each one of those is a decision tree. But many people had other things to do. Some people mix a bunch of models as well, so there is nothing in stone there.
I see.
Think about it as a random force on a different parts of the data.
So how do you warm start that process? So like in the beginning we don't have any labels, right?
Yes.
So how do you do it?
I wanted to avoid that question. So the cold start problem is super interesting, but also hard. It takes us. So this is a class of problem that is extremely unbalanced problem. So the thing is, if I take any random pair from the n square, at 99% is not a match, right? So sampling from the space doesn't work at all. You get only positive examples. Because think of the pair space, don't think on the actual, there is like millions of records, and there are very few pairs from the million square candidate space. So if you start to blindly took from that space, any classifier will tell you everything is non-duplicate with accuracy 99%. So we need to get a balanced selection. So that's why we try to get examples of the negative edges, more important than the examples of the positive edges. The positive edges, or examples of negative means the other way around. The positive edges are hard, and the negative edges is easy. So the negative edges, we get as many as you want by random sampling. But the positive edges, it's only 2 hours of sleep, it requires a little bit more innovation. So we have a paper in AI stats this year that talks about the hardness of this problem and how to do it in correlation cluster. It's a deeper important topic. We're just assuming that somehow we came up with this bootstrapping process, but they were never enough. And because of the difficulty I just said, you don't really cover the whole space. So now I need the whole space to start sample from that space more and ask, are we doing the right thing or not? Till you graduate these people. Make sense?
Yeah.
Okay. Let's go back to that problem that we care about, n square. So community did, have you heard about blocking in Dedup before? Okay, so if I, let's try to be smart and avoid the n square. I need suggestions. And bear in mind, I want all the comparisons. I want the n square answers. I just don't want to do the n square comparison. I want a way to bulk generate n square even in a virtual way, but I would like to get a sense, a concrete, succinct representation of that n square space without doing the n square comparisons. Can you think of any way? Perfect. So hashing, what we like about hashing is this bucketization of things, right? I'd like to bucketize things. But hashing, traditionally, unless you're using the technique I'm just going to tell you about right now, is really invented to hash things away from each other, right? To kind of complete the opposite. I want to randomly hash things. So if I take this and I partition it, by the way, randomly, which I'm going to get into, it doesn't work because you want the across partitions thing. So here's what I want to do. I want to hash it into partitions such that I avoid cross-partition comparisons. That's blocking. And luckily, there are lots of schemes called locality-sensitive hashing. That's exactly this. And locality-sensitive hashing, in general, goes through, think about it as a linear transformation of the data into this hash space, such that what I would like to have is the following. If me and you reside in the same bucket, we should be close. If we reside in different buckets, we should be far. Make sense? And there are schemes for this based on definition of close and far. So you need to tell me what's close and far first. So I'll tell you, let's agree on a definition of close and far, like Jacquard, for example, distance on strings. So I'm going to fix the similarity function to be Jacquard on strings, and then I'm going to do a transformation without actually doing the Jacquard distance. I'll do something else, like take the q-grams, something that I can do in linear time, which is super important. So in linear time, I'm going to assign you a hash bucket using some magical trick, such that if you are in the same bucket, we're very close Jacquard distance. If you're across buckets, we're very far Jacquard distance. Turns out that this is also hard. I cannot get these two together, but I can get one. So we opt for the latter. I'm going to design an LSH scheme such that if we are in different buckets, we are very far away in Jacquard distance. If we are in the same bucket, I say nothing. Okay? Turns out to be very doable, which is getting rid of false negatives, but false positives are allowed. And if I do this, for example, on some scheme on zip, first letters of the name, I can immediately get this from n squared to n squared over m, where m is the number of buckets. S is how many times I do this, because I don't trust any of these things. I don't trust Jacquard alone. I don't trust the address alone. So I can do this for a combination of a definition of closeness and at the same time and columns, correct? And that gives me S different scheme. And I'm happy. I'm going to do S times linear thingy. So now I have my complexity to do this is Sn. But the number of comparisons that I need to do now is n squared over m. Can you guys see where n squared over m coming from? Because I have m buckets in each, yeah, exactly. It's in n over m in each bucket, so it's n squared over m squared in each bucket. I have m of those, so it's n squared over m. Right?
You're assuming a uniform distribution.
I'm assuming a lot of things. It's, this is the
You assume you know the semantics somehow.
yeah.
That's the crucial point.
I'm butchering this right now. Yes, completely. I want to make progress, but yes, you should be very worried about everything I'm saying. So if n squared over m, if m is big, I'm going to say more offending stuff very soon. If m is close to n, then I did dedupe in linear time. If m is close to n, I have so many m, that m is order n. Then I did the dedupe in linear time. Don't repeat this after the class. But that's how, but this is how Tamer makes its money, for example. It's just this. Because you can give me 200 million record, and I can do full dedupe in 11 hours on a machine. Instead of 3. That's why people say, oh, okay, here is a check. Because we have no interest in building the pipelines. And the idea is, as I said, it's not that complicated. It's putting together an active learning pipeline followed by a blocking pipeline on different schemes, making sure it's incrementally updated, making sure that whenever I have a delta, it actually works on all of these things. That's what took all these engineers all these years. There is an interesting problem that some references are there, but I'm happy to dig in any of those. This is by collaboration by my former student, Shu, who now graduated and doesn't have to work with me anymore. And Shu had this we attended a talk by a colleague, and they were talking about optimal join algorithms, and distributed join algorithms, and so on. So the question for you now, if I give you, I would like to distribute these things. So one thing is blocking, appealing to the semantics of closeness to do less work, right? And then for the work that I have to do, because as you mentioned, maybe I don't have a uniform distribution, and one of these buckets are not very nice bucket. Yes? Like, for example, you actually have a clique or something like that. Then I would like to go to distribution. So I'm a generous CTO and a CIO, and said, you can buy all the machines you want from AWS. Buy a 1,000 machine. Do this quickly. What can you do with a 1,000 machine? Million record, 1,000 machine. What can you do? Don't look here. 1,000 machine, million record. Free 1,000 machine. Very embarrassing. You feel like 2,000 machine. I'll tell you what you cannot do. You cannot take the million record and distribute it on the 1,000 machine. It's not going to work. Yes? Because every machine will get a 1,000 record, but you miss all the cross machines comparisons. Remember, I'm going to do the full n square now. There's no blocking. We did the blocking. There's a million record that needs to be compared to each other. And I give you a 1,000 machine to get n square over k. K is 1,000. So I'd like n square over 1,000 speed up. Come on.
Create 1,000 buckets and then put each bucket in each machine.
Yeah, but what do you do across buckets?
You don't have to because you only compare inside the buckets, no?
Yeah, but you're missing, you're missing the other one. I need to finish n square comparisons.
Oh, I see.
I just want to do it in n square over 1,000 time-wise. I want to parallelize it. So I want here the first n square over 1,000, the second n square over, the computation needs to be distributed. Hint, hint. Only that this computation needs to be distributed.
I mean, you copy the data in all the nodes, and then each node is responsible for some of your
Space.
values.
Exactly. So that's exactly how you get n square in one shot. N square over 10. Each machine get the million record. Okay? So nobody's going to talk to anybody. I take a million, take a million. I'm just going to tell you, do the first n square over 1,000, do the second n square over 1,000, and I'm going to distribute it in a clever way. So we got speed up. But we got 1,000x replication. Okay? So we replicated a terabyte, 1,000 terabytes of this. So if it's cheap and it's small, you probably should do this. Much bigger, then there are clever things that you can do. So think about this, this trick. I'm going to think of the machines as if they are in this triangle. They're not, but I'm going to think about it as if they are organized in a triangle like this. Okay? And here's what I'm going to do. For every record, I'm going to pick a random point on that edge. And then I'm going to replicate it only on the L-shaped machines, not on any other machine. Sounds good? And if I do this for every record, I'm telling you, for any pair, there exists a machine that will see that pair. Yeah. Yes. So I will never miss a pair. Any pair you can think about, T1 and T3, there is a machine. T1 and T4, there is a machine. T5 and T7, there is a machine. Okay? I'm going to ask all the machines to do all the comparisons they have. Are you convinced that we covered the n square? Yes? So now, if I tell you that my analysis says that every machine will not see more than n square over k, n over square root of k, n over square root of k, then each machine will do n square over k comparisons. You agree? It just happened that these edges are actually, the length of these edges is square root of k, or the square root of k. Make sense? It's a triangle, so this is actually 2 square root of k. So now, each machine will see n over square root of k, and it will do n square n over square root of k, and it will do n square over k comparisons, which is close to the bound, the maximum you can get. With order square root k replicas. So your 1,000 machine, I'm going to get away with an order of 30 replicas, not 1,000 replica. I saved 970 replicas from the 1,000, and you still get the n square over k. So this is the original algorithm is share algorithm by Ullman about how to do distribution of joins between R and S. And it has very similar idea. Very clever algorithm. And this is just an adaptation with other techniques of how to do the blocking with it in the paper. So the paper is not only this. But it's a clever idea. I thought if you're interested in how to do joins and self-joins on machines with this kind of weird schemes, it's a very set of papers to read. You can start by this paper, but make sense? Okay? We're building up a background. We still, all of this is in the unification data integration land, so we can get it out of our system. Are you guys ready to move on now? Any questions so far, by the way? Yes?
I have a question. So theoretically, you could consider blocking as a hyperparameter of your pipeline, kind of.
Yeah,
right?
absolutely.
So theoretically, you could just, like based on active learning, you could just learn what kind of blocking makes the most sense. Do you do that?
Yes. I just cannot tell you exactly how we do it, but yes, that's in general, in practice, blocking is a high recall, low precision classifier. So you actually build a classifier that have high recall, but you don't care about the precision. And then you're followed by an actual high precision, low recall classifier. And that's how it works. Okay? How are you doing on the sleepiness? Good? Yeah? So we're going to move to even more boring stuff. So come on. So we're going to move to the repairing. So the two examples that I give you right now are matching schemas and deduplication. By the way, in practice, in this large-scale matching on schemas, they actually do it exactly the same pipeline as dedupe. Because if you have that many, if you have hundreds of thousands of columns, columns becomes records. And you run exactly the same machinery on it. So Tamer, for example, have the same machinery in the back end for schema matching and dedupe. It's they call it object linkage system. And a record or a column, it's a thing that has a feature vector. And then you cluster it. So even schema matching is done via transformations and dedupe pipeline. Repair, on the other hand, is a slightly different problem. So we move now to the class 2, which is the repairing of errors and so on. And if you remember from database classes, we talked about something called nulls. Yes? Remember those? Trick questions, three-valued logic. Is null equal null? Is true or false? You see, Paulo's, yeah, that's how I torture them. And you know, we all play that game. And we have also in the theory community, we have really nice work on the interpretation of nulls. And the only bad news for us in general, that the nulls do not exist in reality. They are a dying species. You never see a null. There is always industry would like to do something about this cell. They never leave it alone. So they put something in there to indicate this is a null. I wish they leave it, but they don't. They put NA, 999, arrange, question mark. Like, why the heck are you putting question mark here? If you leave it null, I know it's a null. Question mark's like, by the way, it's a null. I know it's a null, but now it's a string. So because of these things, we get a super interesting set of problems. So I use this example also. Some of you, if you see a talk from me before, that's my favorite example. So my friend, who's a data scientist, would like to visit new places every time. Because he's a data scientist, he looked at the pictures first, geolocated on the map, and this time he wanted to, we all know this exotic West Africa island, no? The name of this island? This island. It's a very famous island. Well, the thing is, all of these pictures are actually were tagged they were tagged 0, 0 to indicate I do not know the location. But unfortunately, 0, 0 is a location. It's there. So unless you actually take a plane and you go to this thing, you're going to be,
Disappointed.
yeah, you're gonna be talking to a ball called Harry for a long time. So, I mean, that is a funny example, but it's a good example of how legal values of null, what I call it. It's a null, but it has a legal value. 999 is a value that can be added. You know, not knowing your salary and putting 999 can screw up the budget. Having 999-999-99 for the phone number can call unwanted numbers in Puerto Rico or something. I don't know. So so the problem of null is actually discovering nulls, discovering what we call true nulls, finding garbage, and that's a big problem in industry. Something that we don't do much. We assume always there is a table with nulls, and I want to work on it. But there is a big step of getting from garbage to null, and then we can put our jazz on top. There are things that are more familiar with, like, for example, integrity constraints. This is a denial constraint, and that says a simple rule, 2 employees. If you don't know what denial constraint is, very, very simple first order logic formula that can tell you, you know, what should be legal and what should not. I'm going to get into this in a while. But think about it, I have a business rule. Denial constraint or not, it doesn't matter. I give you this rule, and I tell you, 2 employees in the same role, if you live in New York City, you should make more money. Because it's freaking expensive, so I want you to be compensated. I would like to make sure that my business people are compensated. So if I tell you find the errors, I'd like to think it's going to take you a few seconds at least, right? What are you doing in these few seconds? Well, you're first applying this business rule like a query. You're generating pairs of people because it talks about 2 employees. You're comparing them to find what goes wrong. So I did this for you, and I identified these cells. Remember, these cells now are not errors. They're just not friends. They cannot coexist together. One of them, at least one of them, is wrong. The reason is Mark White and Mark Lee, they're both employees, and one of them is in New York City making less. So either Mark Lee is not an employee, not living in New York City, or not making 75, or this guy is also in New York City, and maybe this is 8, not 80. Anything can fix that. So that's why it's a violation. It's not an error. It's slightly different than the previous things that we talked about. Okay? We have a lot of papers about this in the community, tons. And they're all nice papers. And they talk about how, if these things are expressed in reality, then how we deal with those things. One more bad news, like nulls, if you go to the chief information officer and you tell him or her, I would like all the integrity constraint, please, especially the denial constraint, you're going to be kicked out of this meeting before it starts. There is, you know, integrity constraints all over the application logic, and it's not in a declarative way, it's a mess. So we need a way to kind of mine this yourself. So let's talk about a little bit quick background on data repair and see where we have very rich, so it's going to be plugs of other people's work and some of our work, and then we can get into details as you will. So there, Shu and I did a paper in Foundations. It's a kind of a survey series. So most of these figures are from that paper. You can, it's on my website. You can get it. But we wanted to classify error detection, error repairing technique based on what is the detect. Are we detecting duplicates? Are we detecting violations of different constraints like function dependency and condition function dependency, what have you? Are we doing automatic or human guided? Is it at the source level or the target level? And we basically, it was our humble attempt to kind of put all the existing work in some sort of a taxonomy to know when I'm reading this paper where exactly it resides. So we're going to talk about an example here of violations of integrity constraints. I don't need to tell this crowd about function dependency and condition function dependency. Anybody? Good. denial constraints very quickly. It's nothing but a way to just talk about a legal instance, like any integrity constraint. I don't want to get into the details of integrity constraints per se, but I'm going to tell you about one of the things that we did before trying to discover these guys, is to try to find a correspondence between the axiomatic reasoning that we did in function dependency in denial constraints. Maybe this implication system allows to also discover them from the data. So here is an example. In this case, it's just a binary, and this is a shorthand for the integrity constraint that tell you, for example, for any two employees, you cannot have city equals city and the state not equal state, which is function dependency. Our friend and the role, it tells you you cannot have two employees. For any tuples T alpha and T beta an employee, you cannot have this conjunctive form, where the roles are similar, one of those same, one of those is New York City, the other one is not New York City, and the one in New York City, which in this case alpha, has a less salary. You cannot have that situation. Once you have it, is a violation. Make sense? So the first thing we wanted to do is to see how to discover and apply these guys. Before I go there, there is a lot of work on integrity constraints. In fact, I claim that 90% of the data cleaning work in the database community was around integrity constraint, because it's interesting and it's close to our heart, and it's to our training, and we can generate more papers, and we graduate a lot of students, so it was good. I'm guilty as well. I mean, Shu made his career out of this, so he should be good. And if you think about how we think about it as a cleaning tool, we go, as you go in the expressiveness of these things, going from something like function dependency, then I up it a little bit, so it's conditional function dependency, then I allow denial constraint, all the way to programmatic interfaces. When I give you a piece of Java that tell you what the integrity constraint is, then this expressiveness help you in putting more strict rules, and you're doing well with it, but also discovering and reasoning becomes extremely, extremely hard. Automating it becomes hard. So, and there is a lot of, I'm not going to do discovery. There is beautiful survey by Felix Neumann group in HPI, and also they have the Metanon project with tons of these algorithms. I think it's one of the greatest surveys they did the community. If you're interested in a discovery algorithm for any of these constraints, you'll probably find it in the Metanon project, at least a starting point. And they did a bunch for the FD. For the DC discovery, so let me give you a quick example of one of the oldest algorithms in DC discovery, which is stain. And the idea there is finding all the function dependency A determines B when A is a set of columns. And this is what we call a schema-driven discovery approach. So I build the space of all possible FDs, and I try to prune them so I don't test all of them. Okay, so it becomes two things. Here is the space, and it's a lattice, because all the left-hand side can be a single column, it can be AB, and so on. And think about this as A determines B kind of thing. A determines B, and so on. And I would like to know, if I know that some of those is correct, can I not check for something else? So for now, if I know that A determines B and B determines C, I don't have to check that A determines C, for example. Stuff like that, okay? It's a little bit more complicated. Tane has a bunch of very complicated pruning rules, but the idea is this is a virtual lattice because it can be big, and I don't want to test every edge on the lattice. And the testing of the edge is very simple, because in order to check if A determines B, all what I need to do is to group by on A, group by on B, and even count, and group by on AB, and I count the partitions. I don't even have to compare anything. Right? So I can very quickly do two things. Decide if A determines B or not, and also reuse the results for something else. So it's a level-by-level algorithm. If you're interested, we can go through it, but it's going to take us all day. The idea there, why I'm mentioning it, because most of the discovery algorithm will be either schema-driven, like this, or data-driven, trying to look for examples from the data. Thin works beautifully if you have massive table that is thin, right? If I have like A, B, C table, then the lattice is a dwarf, and you don't care if you have 200, 300 million records because it's 3, 4 group bys. And it's really bad if you have a fat and short table. Doesn't work very well because you keep testing for stuff that will never happen. And you have 3 records. Look at them and you will know what determines what. So that's why other techniques like FastFD look at the data-driven one, and there are hybrid techniques. For discovering DCs, a few years back, we tried to see if I can also generate a set or discover a set of non-trivial minimal DCs. And we focusing on the one for 2 tuples only. And the idea there in the FastDC algorithm is to generate, so this is an example of a data-driven approach, not a schema-driven approach, or a hybrid. I generate all possible predicates that I would like to put it in the conjunctive form. So these are all the predicates that can be true or false. Okay? And then what I will do is go through this reasoning. Let's assume this is the DC. You cannot have all of these predicates together. Okay? If this DC is correct, then for every tuple pair, Pi, Pj, Pk cannot be true together. Yes? Make sense? Okay. So for every tuple pair, at least one of those is false. Good. So for every tuple pair, at least one of their negation is correct. Okay. So if for every tuple pair I know what's correct, then the minimum hitting set of these is a valid DC. Make sense? Because I want for every pair one of those to be correct. So I want to hit the set of true things for every pair. I don't want to miss a pair. So we transform the discovery problem into a minimum hitting set discovery problem. It's not, and then, okay, then you use your favorite minimum hitting set algorithm and you're fine. And that's what FastDC did. And you can do depth first search, and you use your axiomatic pruning, something like what Tain did, to avoid going through rabbit holes unnecessarily. Okay. The good news is I take a table like this now, and instead of asking your CIO what are the denial constraints that hold, I do something like FastDC, and Felix has even a better algorithm now called Hydra that kind of does sampling and very clever, and it does faster, way faster than FastDC in some techniques. And you can discover a lot of interesting constraints automatically. Many of those are contrived and they do not make any sense because it's an overfitting at its definition. Like we overfit the hell out of this data, right? By definition, I want for every pair to be something correct. So I'm not generalizing anything. I'm just observing and counting. I'm memorizing what's going on. Yes? But still, if you try to limit and rank it somehow to get the non-contrived one, you get pretty reasonable things. Like you'll discover some keys. You will discover that for every tuple in R, it's either have to be S or M. You cannot be not both of those, which is a domain constraint. And you can discover kind of more business logic things that, and even if you don't know what this business logic means. But think about it as a way to do human-in-the-loop data cleaning. And instead of showing people the data, use your integrity constraint mining as a way to communicate with these people. Because if I discover this and I tell you, is it true that all the EDBT school attendees wear red T-shirts? Is a red T-shirt a requirement? Because that's everybody here is in a red T-shirt, for example. And the user say, no, this is not true. You just happen to be in this data. Then I know it's correct or not. It's kind of a high-level interaction. Another thing about error detection of how we also did it in the past, and we're going to come to it, is how we do integrity constraint violation error detection. Because I told you that these are violations. They are not really errors. So how I go from the violation land to the error land. And the wisdom that we use there for since 2009, and Lax and UBC and other people, Leo Petrosi, many people were, and Jan, the idea of overlapping violations was very appealing. So, for example, if I give you zip determine city and I say, okay, zip should determine city, but these 4 cells are not cooperating. They are the same zip, not the same city. So it's a violation. And this is the minimal set of violation. And then I give you another constraint like this employee role business. Then you say, but these also in violation. If I start to put all of these together in a hypergraph, I will discover some bad boys that are in the middle of every fight. They're probably the reason why things are bad, right? So the minimum vertex cover of these hyper edges are a very good starting point to narrow down things. They're probably the bad apple that's causing all of these violations to happen. I made an assumption right now. Can you pull it out for me? This is a big assumption that I just made. It's reasonable. It's not non-reasonable, but it's an assumption.
That we have very little errors.
Right. The errors are way less than, there are less bad than good in general. And there is this sense of minimality. It looks like the error or an error detection method that will discover less errors to be removed is probably preferred algorithm, automatic algorithm. We're going to come back to that for repair, which is more important. There is an interesting piece in error detection before I go to repair that I need to tell you about. How are we doing in time? We have another...
40 minutes.
How much?
40 minutes for the first.
40?
40.
We have more 40 minutes?
Yeah.
Ah, okay. Let's go back 3 slides then. I have time. I was rushing it. Okay, cool. I'll let you early a little bit. Don't worry. Before you melt. An important part that is also not a little bit overlooked in academia, but it's super important in industry, is this idea of where do we detect errors and where errors appear. And I'm going to say a statement right now. This is what I call a big data stack. Every company has something like this. Extraction, ingest box, they create, this is usually S3, and then it go to a kind of a more accessible storage that is indexable, and then you start to go into your data warehouse. Then you start to put it in Tableau. So you go from raw data to structured and extracted data to a little bit more semantics to reporting and aggregation till you see the final results. Okay, we're dealing now, for example, with a market research company. That's what they do. Every company, every big enterprise have that stack somehow.
Silly comment. This is also a small data stack.
Yes. That's, I mean, every one of those you can explode it as you want it to be, and but it's also everywhere. You're absolutely. It's actually our database look like this. Here's the thing. Here is the claim. Where do you think errors get born? Here or here? The first incarnation of errors, is it here or here? It can happen everywhere, right? But the errors that are kind of intrinsic in the data, the dirtiness, not the errors in computation. Here, right? And maybe, maybe not exactly here, but maybe here, right after extraction. Because that's an ugly business right there. Yes? Okay. Where do you think it's easy to spot errors? Here or here? There, right? This is when you see, this guy cannot be better than me. When you aggregate your colleague publications, like he does not have all of these Sigmund papers, something is wrong. He's dumb as a rock. So when I see the final aggregation, I start to see things that are inconsistent. Unfortunately, you cannot go to the Excel sheet. I hope you're not. When you run an experiment at the end, it's like, that cannot be right. Let me... Now it's publishable. So you know that errors happen in your data collection. I cannot just do this at the Excel sheet level, right? You go to jail for this in real life. So we cannot fix data here, but we need to fix it here. But we cannot spot errors here. We need to spot it there. So that creates a problem, because our assumption that I have a table and you need to find the errors and fix it is wrong. Because in reality, you cannot fix the table that you find errors in. So I need a way to go from error detection to error propagation to kind of responsibility and start to blaming sources and blaming input data before I start doing any funky business with destructive evidence stuff. So what pops in your head right now in stuff that we do? Provenance, absolutely. And it's one of the biggest things for provenance is to be able to blame the source for something, at least for data cleaning. Provenance is a way to propagate blame. So multiple people tried, including us, where we wanted to somehow distinguish between where the constraints and where the errors are found. So for example, if traditional error repair algorithm assume that the constraints and the error detection happen only on the target. But we know it's not true, because some constraints make sense here, and some constraints make sense there. So some of the constraints here tells you about aggregation. You cannot have the budget less than the salary of one employee, otherwise people will sue you. But here you can do things like you cannot have multiple addresses. Your birth date cannot be more than 2019, and stuff like that. So you can define integrity constraint all over the stack, and I want to push everybody down. So at some point we wanted to do what this called descriptive and descriptive cleaning. I would like to prescribe a cleaning action, not to actually clean data. I'd like to look at the target and I say, do not let Yanis touch the data after 2 a.m. on Friday, because it looks like all the errors are by Yanis at 2 a.m. Friday, and he's probably not sober enough to put data there. But that's a way of aggregating errors. If I have who entered this and so on. Or stop trusting this source from Wikipedia because it's conflict with everybody else. That allows you to do major actions at the ingest box to prevent this from happening. So a stack like this that we call the DBRX, and it's very limited, so it's really academic in the sense that I don't see it happening. In reality, I'll tell you why, because the assumptions about provenance kill us very quickly. But I would love to do the following. I'd love to do a target where the integrity constraints are defined. I have the sources and I have queries and a way, kind of a stack that generate the target from the sources. Now, I make a big assumption about this, that it's actually an open box. Okay, it's not a closed box. I can look inside and see what happened and I understand it. And you should now tell me stop. I mean, that's already an assumption that we should not listen to you. Because in reality, this is 3-4 libraries of TensorFlow and PyTorch and other complicated things. But let's assume it's a SQL query. If it's a SQL query, then I can detect, get these violations, leverage the semantics that I know what this query is to go back, and I use my provenance technique to be able to reflect back all the involved records in the source that generated that piece. And if I have this connection, automatically I can push the blame down. If this error in the record in the target is erroneous, then all of the involved ones are erroneous, and so on. And then I can do the error detection here. I generate likely errors. Hopefully, I can describe this error by aggregating them. I give explanation to people. People act on the data, and I do this. That would be... And we did it. It's just on a toy thing. We assume that this is our big data stack. And Paolo's going to kill me right now. This is our big data stack. It's not, but that's assume that all the queries look like an aggregation query like this. But even for a small query like that, it's actually hard to distribute the blame. What is the problem in this query? And why provenance will not help us much there? What is the type of query? What type of query this is? And it's an SPJG query. Yes? SPJ is fine. It's just G is not that fine. What's the provenance of count?
Everything.
Everybody. Okay, so if the count is wrong, what can I tell you? Everybody's wrong. Doesn't work. So I need a little bit more than just provenance, who's involved. The formula that tell you all the tuples that involved in the answer is not that useful in aggregation, because everybody's involved in aggregation. So I need a way of kind of causality or responsibility to be able to, okay, if the count or the salary, the maximum salary, for example, is too high, select maximum salary from employee, and the maximum salary came as 4 million a month. I know that everybody is involved in the maximum, but you will look at the people with high salary first, no? So somebody with very high salary is probably more responsible for that error. So there was a paper from MIT at the time called Scorpion that do this with outlier, and this was a way to generate this idea of identifying problematic things in the report, using the provenance to know all of the people that are involved, and then start to see if you can fix them or not. But the idea is to use this idea of distributing blame based on your contribution of the error. So I do processing over the provenance to be able to say, well, yes, we are all in, but I'm contributing more because I have a high salary, and you're contributing less. So again, the details are not important. The important thing is we needed a way to leverage provenance, some idea of responsibility and causality, and I know that the data X-ray tried to do perturbation of the input to see the effect of the output when the provenance is not very well known. It's an extremely open problem that if you're looking for a problem, there is a lot of papers, no good solutions for this, which is provenance for like practical provenance for data cleaning. I know that Susan Davidson is trying to do provenance for machine learning with a bunch of people, and so maybe some results from there. Anyways, and the idea, if you assume that you can push errors all the way to sources, then it's very interesting because these are not like the target, they are likely errors. They are there, they are identified because they are part of a bad thing. So I would like to aggregate them, and there is a lot of interesting work in summarization and building views from answers. Think about it as the inverse query. I'd like to generate a query that tell you where most of the errors are. So there, data summarization, for example, it becomes a coverage problem, right? I would like a query that cover all the red people without covering so many from the non-red people, like a red-blue coverage thing, okay? And you would like it to be succinct and so on. So we identified, for example, few plausible properties. We want high precision. It should be also concise and should have high recall. So you get things like, it looks like most of the error is in the S department. Or it looks like most of the error are people in grade 1. It's not causality at all. It's just a summarization of the error, right? It's just a way for you to just look at these things. Any question about this? No? Okay. So all of this was detection. We just finding errors. Repair was even more exciting because we wanted a way to automatic repair the data. We database people, we do not like a human in the loop. We say we like it so we can get papers, but we don't like human in the loop. We want to do everything automatic in a single query. So that's exactly what we wanted to do. Once you give me the data, I would like to repair it. And the taxonomy that we came up with, the data might be wrong, the rules that generated these errors might be wrong, or both of them can be wrong, right? And the automation, it can be completely automatic or human-guided. And the update model, it can be model-based, so you don't actually repair anything. You describe how to do things, or you do in-place modeling. And there is multiple papers in each of these buckets. So I'm going to just give you an example of an automatic way of doing data repair based on rule-based, not machine learning. This is later today. And data, assuming that the rules are correct. But we have, there are lots of papers. We have a paper, and Fei Chang and Renee had a paper on how to do the both rules and data. They're all interesting papers. So now we needed a guidance to guide us through this darkness of automatic repairing without any guidance at all. I told you, please automatically repair all the data. Here are the errors. And you need to magically come up with something. So we came up with something magically. Is Benny here? No. Don't be offended, Benny, with what's coming. Because me and Benny are fans of minimality of repairs. So here is the thing that we invented, something called the minimality of repairs. How many people heard about minimality of repairs before? Good. So for the rest of you, minimality of repairs is what I just earlier. It's a very interesting concept that makes a lot of sense. If you'd like to repair a data set, how to prevent yourself repairing by deleting everybody? Here is a clean, empty, squeaky clean data set. Here it is. I repaired it. So you should say, no, that's not a good repair. You did too much. Okay, so let's do something that guide that interaction. So I would like, between algorithm A and algorithm B, I'm going to prefer an algorithm A if A did less changes to the data. Make sense? Again, assuming that there are more good than bad in the world, then cleaning by removing, by less destruction is more preferable. Of course, we took that concept and we made it a thing right now, and we created lots of interesting work there that makes a lot of sense. And in a recent paper by Benny and I and others, we actually draw a very good connection between that hard concept and actually maximum likelihood a repair that I'm going to tell you about later. But when things went wrong is when we read too much into that concept from something that makes sense into operational algorithms. So the cardinality minimal repair, for example, tells you if this is an error or these are considered a violation, and I have algorithm A that changed 3, while algorithm B changed these two 3s to 2, both of those are legal instances, yes? This is an illegal instance because A should determine B, and those are in violation. This is okay and this is okay. Under minimality of repair, which one is correct? This one, because it does only one change, while this does 2 changes. How many of you are comfortable with this? Okay, how many of you are not so comfortable with this? Why? I'm interested, not so comfortable, why?
Because I don't know if he chose the right value. I don't know if 3 is the right value.
Right.
2 is the right value.
So while we know that, I prefer this, I wish that this is true. It might not be true. That's what you're saying, right? As if I wish that there are very few errors, and so I'm going to just act on my wish as if it's the right thing.
Because statistically, there is more repetition.
Right. So when saying it, yes, it's a little bit more than that, but might be the right thing, and it's not that much anyways, for example. Here is an example of an error, and then let me ask you, how do you feel about minimality of repair? We all use Excel sheets, yes? How many of you do copy and paste of columns in Excel sheets? Yes? How many of you copied and shifted one cell in an Excel sheet? I'm guilty for sure, and that's why all my students got high marks, and one of them got blank because he was shifted one down. So what is the right action then? To do minimality of repair or change every freaking mark, one up? In this case, actually, the right thing to do is to change all the marks. Right? Don't, this guy is better than this guy, he should get a better mark. No. His mark is right there. Her mark is right under. I need to change every cell. So indeed, minimality was correct, but it was a minimality of action, if you like. So the minimality of repair is a fine, absolutely fine concept. But when you take it to be operational and do it like this, sometimes it creates really bad results. But for the lack of other guidance, it was the only thing we have so far. People relax this concept into other things. For example, we treat this as a very fine repair under a different set of a different semantics called set minimality. So under set minimality, not cardinality minimality, the set of changes has to be minimal. In the sense that I cannot revert any of them back and you still get a repair. Like these are kind of the smallest necessary changes if you need to touch these cells. So I'm going to also allow it. Both ensuring cardinality minimal and set minimal and something that we invented called cardinality set minimal, all of those are hard problems. because, you know, you can immediately see, I'm going to go through all possible repairs, and I pick the one that are minimal repairs. Anyways, but it's, so for example, I need to choose things like that, and so under this, let's assume that minimality is okay, because we don't have any better thing to do. So one of the repair algorithms that assume denial constraints, for example, are your roots. Yes?
Just have a question.
Sure.
About the other.
Yes.
Do you have any evaluation that how many repairs does it goes well on?
Yeah, so we did this evaluation in a IEEE bulletin with my very former student, George Biscalis, the one that did the Tamer with me. And the recall was 0.02, like less than 1%. Like that, it was bad in most data sets.
So it depends, maybe it depends on the source of the data, right? If it's
No, here's the problem. The problem is sometimes there are so many minimal repairs, and you need to give me one. That's the first problem. And the second, that might be the right repair is not even a minimal repair. And so you lose. It's a good concept, but if you go and say, okay, I'll give you the minimal repair, it's a good exercise, but you might miss. That's the problem. So we need a way to act on this concept of minimal repair without actually reading too much into it to try to make, okay, I'll give you the absolute minimal repair. And I like it because it's an NP-hard problem, and I can go and get 2 pods and Sigma paper from it. Because it doesn't work. So here is an example why it doesn't work, for example, or what we try to do. And remember this picture when we did for error detection, when we put all of these hyper edges on top of each other to find go from violations to errors. Remember, this thing was a violation of the blue one were the violations of this constraint, the red one was the violations of the function dependency. Under minimality of repair, you should minimize the number of cells that you need to touch to resolve these hyper edges. Make sense? So before I go there, if I tell you repair and you're not a database guy, or a database person, what is the first thing that comes to your head? What is a repair for us? Here is the data set, here are the errors, and here are the rules. It's a rule-based repair. Please make this database consistent with these constraints. What is the first thing that comes to your head? It's a what problem? What is a task? Here is a data set. Here is a bunch of rules. Make this agrees with this. We need to update the value, but what is the problem? Anybody can see it as a SAT problem? Can you see this as a satisfaction problem? Yes? So I can probably generate clauses inspired by these things, and I would like to find assignments that satisfy these constraints. Does it make sense? Okay. What is the problem of hitting it with a SAT solver? You know how good SAT solvers are now. They're really good. So what is the problem that we just don't hit it with a SAT solver? Because SAT solvers do not care about minimality. Right? It will find an assignment even if it invent a new value for every random variable you have. Yes? It will just pick one from the domain, pick one from the domain, pick one from the domain. And he said, here it is, an instance that is satisfying. So you might go to MaxSat and other things, but they are less efficient. So we tried all of this. It blew in our head. It doesn't work. So minimality and this can be combined together. I'm going to do this minimum vertex cover things. So now I see the whole space as a big hypergraph with hyper edges with overlapping stuff. So I started to see islands of correlated pieces, yes? And then I do local SAT solvers in each. So this local solution is more efficient and adhere to minimality because I'm going to build satisfaction clauses only around the minimum vertex cover, not among everybody. And I keep increasing till I find an assignment. That was the whole idea about this repair algorithm that we forgot we published when. It was, I think, 2013. You see the trick now? I get all your constraints, all your rules. I do hypergraph representation so I see the minimum pieces that are involved. and I try to find an assignment for these small pieces that make them disappear. So this is what we're going to do. Generate a repair requirement, and, for example, reverse all of these constraints, make T1 state equal T3 state, or make T1 state not equal T2 state, and so on. And then I try to find an assignment, and for example, looking at all of this and say, you know what, if I change this to Arizona, everybody will be happy. So that's an assignment that will resolve all of these constraints, make everybody satisfaction. In this case, the function dependency, the red one, is satisfied. And these two, one of those guys are not in New York anymore, so we don't care. And we're done.
But how accurate the data will be? Because
we don't care. It's satisfying the constraint.
no, but there is a reason that the constraints were not satisfied.
Yeah, we also don't care. That's the problem. What you're just saying right now is the problem. We didn't care about any of this.
I see. But then why are you doing this?
To publish in Sigmund. What's wrong with you?
Fair enough.
What is the part that you didn't get? We're not doing this for... We're going to do the commercial one later in the part 2. No, it's the idea is to... we need, in the lack of any other guidance, this is the best you can do. So basically, here is what... We don't have any other way of going around this. Right? How do you know it's correct? And, you're maintaining this. Is it actually the source that removed? We don't know. Somebody give you all of these and said they're not conforming with the constraint. So you're basically saying, I'm going to surgically change the fewest possible to make it consistent. Is that good enough? And that's a good start. Because by changing also the minimum, you might not screw up the statistical property that much. So it has a lot of plausible properties. We're going to build on this heavily later. But the problem is just we overdid it. That's the takeaway. And because of we overdid it, we didn't look at other sources of important signals. For example, is there a nearby data set that looks like this and how it looks like? This is mentioned somewhere else? If I put Arizona here, did I screw up the distribution of states in the data? How many other people are with Arizona? Is Arizona co-occur with, is so many ands in Arizona? Is like this first name is popular in Arizona? For example, like imagine that these are countries, for example, right? And you say, you know what? Ann Nash is born in Egypt. That sounds unlikely, right? We might have Ann Nash, but in Egypt, but it's probably not going to be born in Egypt. So we missed other things. We just focused on one piece, which is the rule-based one. Ironically, this paper was called holistic data cleaning, but it was not. We want it to be holistic data. Yes?
But I see that maybe semantics can help in these
Yeah.
repairs.
Yes. We can think, and all of you can think of things that can help. The trick is not that. The trick is whatever you're thinking about, how are you going to inject it in this case? Like the signals are not that hard to think about. The signals are known. Statistical property, the semantics. How are you going to represent it in an automatic algorithm?
But just annotation can solve this.
Annotation is not automatic, my friend. Annotation.
But yeah, nowadays we have some automatic. Yeah, it could be semi-automatic.
Right. Let's assume that I annotated everything. Then what?
Yeah, but with this annotation, you could make even similarities. Based
Yeah.
on
Again, I get it. We can annotate. We can compute all the similarities. Then what do? You have multiple things telling you multiple things, different things. So the first thing we do after we do this mess is we do something majority vote. We screw it up some other way. We're very good at this. So we need to. But anyways, we're going to build a little bit more principled way. But all of this is the right track. Are we good? Are we doing well? Okay. So it is our attempt in 2015. We wanted to build a system that allow people not to think about cleaning anymore. And I'm proud of the system because it's the first. I'm not so proud because it never got deployed for a good reason. So here is the idea of, how many of you know GIST or heard about GIST? For the old people in the room, no? So GIST is, you know which GIST? Not the, okay. Generalized search trees? Yeah, awesome. Perfect. Generalized index search trees. And it's part of Postgres right now. If you go to Postgres, and you're looking for B trees, there is a gist things there. Gist was an idea came from Berkeley 1995 by realizing that B trees and R trees and it was the tree era where everybody and his dog had a tree. And we wanted to say, oh, they all look like this and they all look like B trees. So we make it extensible by saying there is a core algorithm and there is a bunch of customization code that make any tree using the same core a new tree. So you build it once in Postgres, and you can build your own tree by just writing this extension. It was brilliant. It was very nice. And it's now part of Postgres. And the first project in my PhD, we took gist and we make it something similar to it in space partitioning trees called SPGist. And then it's now also part of Postgres. So you'll find SPGist in there. That was a paper that we did in 1999. And 2 Russians got excited about it and put it in Postgres. So we liked that idea. We wanted to continue. If I can do a cleaning system that is extensible, so I build the repair and everything, you just tell me the rules. You just tell me what makes an error and how do you think you should violate it, and I compile them together, then maybe it will be a good service for the community. So that was the Nadif algorithm, and it was what I was telling you about. This SAT solver was here in the core. We discovered the denial constraint using fast. We put all the pieces together. It's just this part never scaled. And it's also built on minimality. So it didn't work. It didn't work that well for all the combination of the challenges that I told you about today. The mining was contrived. But if you run denial constraint discovery on a large data set, you can get hundreds of thousands of rules if you're not careful. These things can care only about rules. Nadif looked like this. It has a core, and then you build these extensions. So you build something called value and fix, scope, iterate, block, which is kind of an interface, generic interface that you extend and you write your own. It's exactly like gist. And then you compile them together. So here is an example. For example, you say, here is my implementation of value. It takes a tuple. And if the country code is 31 and the country is not Netherlands or Holland, they return an error. So basically, it's my error detection logic. It's a way to generate errors. And to fix it, just put I put a a fix algorithm here is trust the zip code, trust the country code. So if the country code is 31, just put Netherlands in the country, something like that. It's just an example. And we assume that people writing these rules is going to fix the data. So you can see the limitations, right? You wanted to automate it, so you made a lot of assumptions. Okay. I don't know about you, but I'm tired. So we're going to stop here. I'm going to tell you about this. This is a new, I think it's available for, like if you're at a university, you can get this book. I assume all universities have it for free, and if you don't, I think I have an author copy that I can give you, unless you want to buy it. Let me give you a copy. No, it's not. But anyways, it's really the author copy. I can. It's a book that have all of the things that I talked about today and the things I'm going to talk about next time as well. It's a good kind of a more reading material to tell you where things is. But I'd like you to think about data cleaning as this life cycle where I have data and I would like to have some quality rules. And I call it quality rules, but I actually can call it semantics. Think about all the semantics that either can be declared or mined from the data. And usually there is an error detection piece that generates your hypothesis about what an error is. You try to do your best to repair it. You shove it again in the data. That's what people do daily in enterprise. That's their life cycle. And we're going to talk about most of these boxes. So in this first part, we talked about one example of mining some of these constraints. We can mine FDs, we can mine DCs, we can mine things here. Now you have some semantics. Error detection, you can do whatever, deduplication is an error detection. Accumulating violations on top of each other and doing minimum vertex cover is some sort of error detection. But also outlier detection and running address doctor and finding typos, all of this is error detection. And the idea is, what do I do with all of these errors? I need to kind of repair. This repair box can be anything you want as well. It can be rule-based cleaning, like what we talked about, and you generate your Sigma papers. But it can be also, what people do here is all over the map, from building interfaces to send to experts so they can manually repair it, or running Perl scripts on strings, or their own rule-based system, massive rule-based system, 500 rules. I think GE had more than 500 rules, for example, in this repair. So we'll try, and we told you some examples there. So in that first part, it's all kind of understanding the components of these things. But I would like you to get an appreciation of they do not work in practice, not because they are bad ideas. In fact, they're all, in my opinion, seminal work has been done in the theory community for this. It's just execution on it was a little bit more verbatim. We took minimality and we made it an algorithm. We took FD discovery and we made it an algorithm, as opposed to thinking about all of these as signals for data cleaning. And that's what we're going to do in the second part of the lecture, where we're going to talk about how to do this as an inference problem. So it's going to be a pure machine learning thing, but I'm going to be dropping database terms that we talked about today. So we're going to talk why this was never adopted and how to leverage this in building a working model. Okay? Can we take more questions now, if you like general questions, more background that you guys need? And then I know that we don't have a formal challenge on the website, mainly because I'm lazy, but I can tell you about a few things that we can do after second lecture. So in second lecture, we're going to talk about an open source project. So it has it's on GitHub, and I'm going to give you a few things that if you're interested, or a group of you is interested, I know exactly what's missing, and can give you tomorrow to do it. Very easy. And then we talk about it later. So that's my idea of a challenge. So we're going to talk about this in the next lecture as well. Any questions? No? Okay. Since the first lecture was a long time ago, the first half hour is a recap. No, it's not. Remember we talked about this, and we wanted to do build solutions that kind of handle these two distinct classes. I'm going to show you that they are not only two classes, but these are the two main ones. This is more data unification, as I said, more engineering. The classification problem there, or machine learning there, is kind of very well understood. And I know that I told you for data deduplication, we do kind of feature engineering and feature vector. There are a few papers in the last year or so about using deep learning and neural networks for dedupe, and I'm going to talk a little bit about neural network implementation of those. And they have very different requirements in terms of training data. So there is still remain to be seen. For deduplication, still the best algorithms are random forests and things like that. So it's not clear to us that deduplication will need deep neural network unless you're talking about records that are extremely fat and text heavy. And in this case, we need a representation layer that allow to capture this. But anyways, I didn't talk much about that. And hopefully, I also cleaning or repairing has to do with this outlier detection. And the stuff that I talked about last time, unfortunately, in reality, they cannot or they do not exist in isolation, which is a big assumption that we made in our papers. And I think it's one of the reasons why it didn't got adopted. Put yourself in the shoe of an IT engineer where they want to actually clean a data set like this. This is what they get. They're not going to take the time and tell you, oh, let me read shoe paper on deduplication and build a system for deduplication to remove duplicates, and then read this other paper from VLDB about outlier detection. Then I'm going to read this paper from NeurIPS about all of these things coexist together. So they have duplicates. There are value and syntactic errors like mistype, like a typo here in New York. It has missing values or other garbage in there. And as we said, integrity constraint violation, when it's not really, we don't know if even an error, because they agree on the same zip code and these two different cities. Actually, in this particular case, even this zip code has nothing to do with the two cities. So it can be very garbage. However, we want to go from this picture to a picture that consolidates duplicates, change typos, impute missing values, and suggest a way to kind of clean all of this together such that this data is ready data to be able to move down to Tableau and get the pretty picture. That's the real exercise, is to do all of these together in an exercise. For multiple reasons, because these fixes actually conflict with each other. Like the fact that you know that these are duplicates might remove all the violations that these things do with other things. For example, for violation detection. Or when you remove the violations, it will be much easier to find duplicates. So thinking about errors as different nails whenever you have different hammers didn't serve us very well. So as I said, we try to do so many, there are so many papers, and this is just even just selection of my students' paper, and it's a lot, and we still, and you can see they're going from 2013 and what have you. But today I'm going to focus more on this new idea or new way of thinking about errors, which a very proud piece of work that Benny and Theo and other collaborators led the work, but I'm very happy to be part of that team. I'm going to tell you about the HoloClean open source and why it's a new way to think about all of these problems and why it works or not. And the latest thing is HoloDetect in 2019, and see if there is a new way that we can think about to kind of move our understanding of the problem. So we're going to talk about machine learning for this problem. That's what we're going to talk about today. And I don't want to give the impression that, yeah, machine learning is new, let's use it for data cleaning. Machine learning has been used for data cleaning since the 90s. It's not new. As I told you, the earliest paper was Sunita Sarawagi's paper in the 1990s about using active learning for dedupe. So it's not, it's not anybody's invention. The reason it's coming back again is because of the tooling around ML systems now has become really, really easy for us or any of us to build your own stack. It does not require 3-4 courses in machine learning and you build your own inference, for example. You can now, with 100 lines of code, you can have a working end-to-end pipeline with logistic regression and training and what have you. So that tooling that came around machine learning made us, can we rethink data cleaning and data unification as actually a machine learning problem? Because it is. It's an inference problem. So I'm going to give you 3 examples of this. And I already give you one. Tamer is an example of unification. HoloClean is an example of cleaning. The third class that I didn't talk about today, and it's a nice sister to data cleaning and data repair, is data transformation. And you can think about it as repair or cleaning or not. And a good example of it is Trifacta, which is the commercial product of Data Wrangler out of Berkeley. And these guys think about how to build an Excel sheet on a steroid by telling, oh, this column is related to it, here is examples, and I figure out how to go from one to the other, right? Building transformations, and extremely useful in industry because I would like the transformation of units, syntax, computed attributes, and I would like you to use the induction to do this for us. So it's a lot of program synthesis and predictive transformation, a lot of user interaction. But I'm not gonna talk about it today. I'm gonna talk about mainly these two. So we talked about the record linkage and how it's and why this is so easy, because that's the main problem, is just to build that classifier and to tell you a match or not match. So that's a data unification task, and let's just leave it as is. And we know that this is what kills us and what have. So I'm not gonna repeat any of that. So let's assume that we have a duplicate-free data. for the sake of argument right now. I'm going to tell you later that we don't need even this step, but let's assume to get these out of the picture that we remove duplicates, and now we have mentions of independent things, that they are correlated but without repetition. Then we haven't solved any of the other things, because we tried in the first part of the talk this morning, we tried all of these rule-based, and we fixed each one of those alone, and that didn't work that well. 10 years ago, there was a big wave in database community about probabilistic database. Anybody got drank from that Kool-Aid for a while? The problem is there, we found this idea of probabilistic reasoning of uncertainty as a very interesting problem, and it makes a lot of sense. And I had a student graduating from this, and you know, it makes sense that I reason about uncertain data as a probabilistic data. Every cell became a random variable, and now I start to have a domain that it ranges over, and I can talk about probability distribution and even marginals, and I can talk about joint probability distribution. That's a very nice way to go away from a logical interpretation of what's going on, and I go to a much more permissive land of probabilistic interpretation of what's going on. This can be true, this can be true, and I have a solid mathematical background that I lean on to give me numbers that are actually probabilities. And instead of inventing things that look between 0 and 1, and I call them probabilities. Our biggest mistake there is we didn't, in my opinion, that we didn't think about the generative process. Most of the the probabilistic database papers started by marginals on the tuples. We start by a probabilistic database where these are independent tuples and the probability of each tuple is 0.9, 0.6, and nobody tells you where these probabilities are coming from. And then we liked the exercise of computing the probability of the output, and safe queries and not safe queries, and when you can do multiplication and when you don't, and these kind of things. It was very interesting work, but I think we missed out on thinking about what is the generative process that generated this data, where is the randomness coming from, and why what we're having are probabilities. The other problem that why this work didn't take off is the inference engines for probabilistic database were also very limited. Like if you're building, if you're saying, I remember work in IBM when they wanted to do selectivity estimation. This is when Yanis and I, for a long time, were interning in IBM, and other people wanted to do the selectivity of queries and say, let's talk about it as a big Markov network. For example, I get the joint probability distributions of the columns, and then if you tell me any question, I can ask the model, and I give you the probability of that predicate. Think about selectivity estimation as querying a PGM, right? I'm interested in people age blah and blah and living in New York. That's a query of the probability of randomly selecting that predicate from the database. So if I have the joint probability distribution, I can answer this, and no need for this garbage statistics and all the assumptions that we did in database engines about independence and so on. Also didn't work because we didn't know how to scale inference engines. Because if I want, like it's okay for 200, 300 attributes, but if you have millions and millions of random variables with weird correlations and structure in them, to take all the time to build this big Markov network, for example, or big factor graph, you know, you're not going to have enough time or resources. And things has changed. So these are opportunities, as I said. Opportunity number one, that we know that rule-based repair, the way I told you before, didn't work. However, it carries some interesting problem. So we know that the problem is may not fix errors, and it can introduce new ones because it read too much into this idea of minimality. So opportunity number one, can I take minimality into a probabilistic principle that can make inference faster? So instead of taking minimality as a constraint, a hard constraint, so I produce only cardinality minimal repair, can I actually be truthful to how it's invented as a guiding principle, and I put it as a probabilistic concept? So this is opportunity number one. Opportunity number two, there is a lot of people that didn't believe in this business of automatic repairing, and they said, no, I'm going to do only trusted repairs. I repair things if there is a master database or a master things, master record store that I can query, and only if it's there I can repair my data. In industry, it's called MDM, or master data management. It's a big deal. It's how Informatica made billions of dollars, is to build these master MDM solutions. The problem with this, that mapping to external input, that external knowledge bases had very little coverage to transaction data, the new data that comes every day. So it's very good in getting the dimensions right, but at the transaction level, I'm seeing a new customer, I'm seeing a new address. And if there is an error, external data cannot help you. So also was a problem, but it's an opportunity, because I should not ignore trusted data sources, maybe as training data and a good example that I can build on it for the things I don't trust. So I'm going to show you how you're going to leverage that in a second. So the good thing about using ML for curation is few interesting principles. First, I can combine all the signals that I told you about in the first lecture. If you're violating, let's assume that I'm a random variable, and you'd like to figure out my name is a random variable. So before I ask what is the most probable name I have, I can ask few things. Am I violating any constraint with anybody else? Did I co-occur enough with my other attributes? Do I look like an outlying name? Is there any name that is so close to me that it's more likely that I'm a typo? My current name is a typo. All of these signals, I can put it together under one umbrella, and I do inference as different biases in the system. So think about it that in the beginning, every random variable over a domain, all the values in that domain are equiprobable. I can be anything, you can be anything, right? That's zero knowledge. All what I know is your domain. So your name can be anything. Then I say one signal, and all of a sudden I'm having a bump in that distribution. Few names become less probable, few names become more probable. Then I say one more thing. Then you have more bias. And I say one more thing, more bias, till I get a peak closer to what your value is. And that's what I want to do. And this is a very different way of thinking, because I'm moving from the hard constraint land to the soft constraint land that just influence the probability of certain values that you can take. The only difficulty is if your value also depends on the value of the random variable next to you, I might need to figure out this together. So now I need to kind of reason about how you're correlating together. So this is a good opportunity. It's good that I avoid the rule-based systems completely. And this is not a good, what I really meant here is avoiding rule-based systems, not avoiding rules per se, because I had this discussion in the break. Rule-based systems is the worst that industry would like to get rid of, because that monster keep growing, and they call it the technical debt of the company. Because whenever you grow, no rules get deleted. Nobody dares to delete a rule, because Jack was here before, and Mary was here before, and she wrote it for something, and I'm going to put another rule. And they have this if-then and priorities, and become a beast with thousands of rules, and I'm not kidding. We've seen it in many, many customers. So handling that rule-based system as a logic, as a kind of a hand-written SAT solver is a nightmare. If I can use all of these rules, and instead of rule-based system complex logic as just adding bias to the system, would be nice. And more importantly, I can communicate confidence, which is super important. I can communicate confidence in a principled way. I can give you something that I can stand behind. I cannot say, this is 0.6 confidence. You need to interpret what that means. It has to have a statement. A common mistake, for example, if you use naive Bayes, for example, there is you guys know what the Fibril, there is an open source for deduplication a long time ago called Fibril, and it's a naive Bayes tool that you put, you know about this because you probably use it, and it's a generated data set, and it has a classifier, and it gives you the probability of a match given the feature, the probability of a not match given the feature. One of the common mistakes is to interpret these probabilities as confidences. They're not. They are a conditional probability on the feature that you see, and communicating it as confidence is just wrong, because there are multiple numbers of those as well, and they do not mean the confidence that the user expects. But anyways, the challenges are, the challenges are the opportunities at the same time. We don't know how to compile these evidence into features. We don't know how to take denial constraint and make it a probabilistic statement. We don't know how to take outlier detection and make it work well with denial constraint. So we need to be innovative. And if you're telling me, okay, let's assume that I have all of these things and I'm building a massive model that is capable of telling me what's right, what's wrong, and how things should be. I need to train that model. And if things are as complex as I tell you it is, then you should expect this model to be complex, yes? Which basically means training data, yes? And I just told you that there is not enough errors and there are more good than bad. So if I find all the errors to train a model, I defeat the purpose. It's a chicken and egg, right? I need a lot of examples to train a model that is capable of finding the other errors. And the errors are that many in a heavy imbalance problem. So training data is a challenge. And if you ignore training data, you need to be able to run robust modeling, robust models that can deal with noisy observations. So that's another challenge, because you're building models that will see dirty data to fix yourself. So you're building a self-cleaning tool kind of thing. And if you solve all of these problems, we definitely have to solve the scale problem. We have millions, if not hundreds of millions of random variables. So putting it in your year 4 of university inference engine that you build in your machine learning course is not going to work. Loading these things in memory and building a factor graph and run inference on it, it's not going to work.
What about the explainability? Because you talk about the confidence, which is a nice thing to have already.
Right.
But I guess when you correct something, when you say this is an error and this is a correction.
Is that the second question you ask about something that I would like to avoid?
No.
Okay. Yeah, so I like to talk about explainability, and I do not want to talk about explainability. Explainability is one of these philosophical topics. But we can talk about, yes. Yes, it's a problem. Can we talk about it in a while? It's an interesting discussion. I'd like to pick your brain on what explainability means. And I mean, for every solution, there is a simple explainable, for every problem, there is a simple explainable solution that is wrong, yes? So sometimes you need to. So this is I'm not sure if I can show this under recording, but I'm going to tell you that it's. But anyways, I don't. Maybe there. It's not going to be shared in public, so it's fine. No, what's funny is not the picture itself. What's funny, it was sent to me by the person who's running announcement in our department that didn't know anything about machine learning or data quality. And he said, you keep talking, mumbling in the corridors about this. It's a bad thing. And he sent it to the whole group in Waterloo in the announcement. So it's like, apparently data cleaning is a punishment in the machine learning world. So I'll tell you why it's not the same. So why it's a hard problem? We need to deal with this data sparsity problem. We talked about errors. Data is heavily structured. And one way to understand data sparsity, why this problem is sparse in structured data, because this topic is about structured data. We're not talking about videos and images and cat and dog and Google stuff. We're talking about boring enterprise data with 200 columns and Excel sheets, right? This is where the money is. I'd like to close your eyes and think about an Excel sheet with 200 columns as a space. As every column is a dimension in a space, and every record is a dot in that space. Close your eyes and tell me if this space is empty or dense.
Empty.
Massive empty. There's nothing in there, right? It's worse than our universe. These are 200 dimensions, and there is a point here and point there. So the number of points that we have giving the volume of the possible domain. So you cannot learn anything, basically. You look at this, and there is nothing you can learn from if you're trying to just depend on co-occurrence and things. You need to be a little bit explicit about the structure. The good news is that this visualization that I just told you about, I cheated you, because I hide from you all the structure that there is explicitly with this data as well, right? It's not the only thing we know about this data, it's just the records and the domain. We know what's the structure, what depends on what. We need function dependency. We know the non-constraints. We know rules. So it's not a completely random space. It's a heavily structured space. And if you add the structure on that emptiness, you get a massive opportunity for inference. Does that make sense, what I just said? You guys following what I just said now? Okay, we're going to come back to this point because it's important. The other important thing is, in order to make that space go away, is what I just telling you about. How do I encode the background knowledge, structure, constraints, what you know about the data into the system, and scaling? This is kind of a bad drawing of how the space, how you're going to see an Excel sheet if you think it's a probabilistic graphical model. So every dot here is a cell in an Excel sheet. And every line between two cells is the value of this cell depends somehow on the value of other cell. So this is how a probabilistic graphical model will look like if you visualize it. It's like a massive piece of a hairball of things, and you need to run inference on this. So in 2017, we published this paper called HoloClean, and the idea there was, can I run repair, not detection? Let's simplify things to understand what's going on. And repair will run it as an inference problem. So somebody already told us, these are the errors, and this is the non-errors. Or this is, I have confidence in this data. I don't have confidence in this data. Can you learn a model from the trusted piece to fix the non-trusted piece? Make sense? So we're not going to do denial, and you have the denial constraints and the matching dependency. So you wanted to take this as an input. We take the data set that we wanted to clean, all the denial constraint that you want, if there is external information, if there are matching dependency, whatever you want as an input is an input. And I would like to take this, run an error detection module, and I'm cheating right now, that assuming that this is a good error detection module that will tell you this is untrusted, this is trusted. It's okay to have false positives, it's fine, but I'm assuming now that these are all the errors. And then I'm going to have a compilation module that will take all of this and compile it into a joint probability distribution of the data. And then I'm going to run inference, which is the repair for us, become nothing but asking what is the most likely value for every random variable, like running MLE on every random variable. And that becomes my repair. We tried this, and it worked very well. It worked better than most current solutions, not because we are very smart, because it was the only tool that attempted to take all of these together into account in a kind of an easy way. So the tools that we compared against did only one of those. So it's not surprising that we won. It's surprising that we made it work together. So before I tell you about this, there is this piece that appeared last year in ICDT. And Benny had a big contribution in it. And Chris is a machine learning theoretician as well. And Theo and Chris are my co-authors in HoloClean. So, but really, Benny and Theo did most of the work on this paper. The idea is, can we think, and why this came 2 years later? Because after HoloClean worked, we wanted to sit down and say, like, why the heck this worked? And so we came up with the theory after, which is very typical. So here is, I'm going to simplify this, at least for me and for you. How do you think about this data cleaning problem as an actually inference problem? We're going to adopt something called the noisy channel model, in which we're going to think about the world and how data was generated, how it got polluted, what is it that we're observing, and can we recover the signal that we lost? So without offending anybody in the room, we are assuming that God created data clean. Okay? And the devil came and messed with this data, and we're seeing the devil's work that screws the good work of God. If you're offended, this is a data God and this is a data devil. So that's no. And then what we're seeing is this J star, an observed instance after a lot of pollution. Make sense? So if I can model the devil by parameterizing it, model the data God by parameterizing the data God as well, and look at J star and recover my estimate of these parameters, then I figured out the creation and the pollution process. and I figure out the creation and the pollution process, I can estimate what the devil works and what God intended for this data to be. So for me, repair becomes nothing but what is the instance, the possible instance among all possible words of how this data was created, what is the most probable one giving what I'm observing. And this is nothing but probability of I given j, right? But if writing it this way, this is the prior, this is what I think I know about how I is, and this is something that I can see and compute from the observed data set. Make sense? Okay, so the details will be the two cheating points that we just did right there, because we went from something that is we all agree on to something that we should start disagreeing. What are these deltas? What are this theta? Because how good this is depends on how good my modeling is, right? If I model the very simplistic devil, very simplistic generative process, I'm going to get a very simplistic part of the word, and I tell you something wrong, right? The other thing that I would like you to appreciate, because you can always read the paper about the details, that as this gets more complicated and you're closer to reality, learning those becomes harder and more demanding. So there is a natural trade-off here in what you want to do. So here is an example of, this is the dirty data instance here. And instead of going backwards, I'm going to assume that it was generated this way. For example, this is my schema and constraints. And this is a very simple creation model, but it's powerful. Imagine that the kind of tuple IDs came, like all of the tuples can be tuple membership that are completely independent. So I can generate all possible words by independently picking things from the domain. And I have a bunch of constraints that start to put a probability distribution over this. So there will be more likely word than others. So if I have my word only as independent tuples, then all possible words are possible. You agree? If I have a bunch of constraints and I put it, then I can see distributions, and there will be words that have more probable than others. Yes? And if I need to parameterize that model and I figure out the parameter of this model, I can compute the probability of a certain word. What is the probability of seeing this? What is the probability of seeing that? And then so this is, assume that this is a sample word that can be created. For every word that gets created, we assume that there is a process, that this realizer, this polluter. And that polluter in this case, think about a polluter that does the following. It will go for every tuple, it will go for every cell, and flip a coin with probability 0.1, a bias coin. And if it's heads, it's going to mess with the value. And if it tails, it's going to leave it alone and move on. So it's an independent polluter. Okay? So now I have a generation process that's kind of guided by these constraints. And I have a polluter that kind of independently mess up with things, and that will be the output for this instance. The task is, if I see this and I assume that this exists, can I come up with this? So that becomes the repairing process. Okay, I made some gross assumptions in the middle, but that's kind of layman version. Any questions about this? Make any sense? Does it make sense to you? Is it plausible?
Intentional model outputs a joint probability.
This process reports a world. It just gives you a possible database. But we just don't know which one it is.
Okay.
But for each one of those, it's going to be polluted in a specific way. So if I know this, I would like to kind of reverse engineer that. And I say, what is the most probable I that when polluted, it will produce this? Right? One of the simplistic assumptions that I did right now is this independent polluter, because you might think of a systematic polluter. Right? A polluter that once it pick a cell and messes with you, it messes with all the other cells in that record with high probability than some other random record. Or it always messes with this attribute whenever it messes with this attribute. Or it doesn't randomly change your value, it copies it from the one next to you. Right? So I can be as complicated as I want, but for the sake of argument, this is it. Go ahead.
The
Correct.
How likely is a person to be of 2.1 meters high?
With his name is this, yes, yes.
How likely it is that many people live in the exact same address?
Yes, absolutely. And it's going to probably be clearer when we get an instance of this intention model in Holoclean, because that's exactly what we assume. So, for example, here is what Benny was just talking about. So if I have these constraints, so I have this, like according to the independent tuple generation model, the probability of any word is just the multiplication, because they're independent, of any tuple that I see, and the not seeing the tuples that are absent. So if I have a universe of tuples that I can select from, then whenever I see something, and they're all independent, that's how I do it. If I assume that there is also a set of constraints, and let's assume that this set of constraints it's a function that, for example, the violation of integrity constraint can be one of these constraints. Then the full probability of any I can use an exponential family, for example, that tell you that it's that kind of part, the independent part, plus an exponential part that can kind of try to penalize things that are violating. This is nothing but e to the power of, for every constraint, the weight of that constraint, of the function of that constraint. And the function here is the violations of that constraint, for example. W's are the weight of every constraint, and it takes every constraint and map it to a weight that can be 0 and 1. Let's assume it's positive weight. So if I have the importance of every constraint, I'm going to have a proxy, which is the number of violations that constraint is, and I'm going to multiply it by how important this constraint is. If we are in the hard constraint land, this W is always max. You agree? But if there are constraints that are approximates, that I would like it, then I assume that this can be anything between 0 and 1. Z is a partitioning function, which is basically to make things be a probability distribution. Z is nothing but sigma over all possible words for this. So now, the only thing missing from here is just figuring out this W. Right? These are the only parameters of this model, the importance of every constraint. And I probably can learn this from the good world, right? So from the good instance, I can probably learn that if you give me a lot of good instances. So now I have the intention model, and that's exactly what Benny said, will give you the likelihood of anything you ask that model is. Not only the probability of a word, but also probability of anything coexist together. Does that make sense so far? So I turned a bunch of constraints, first from hard constraint to soft constraint, to learnable soft constraint, to an intention model that generates the data, not a quality constraint after the fact. So it becomes part of the generative process. The pollution model is not important, but anyways, now when I combine these things together and I observe a J, I would like to get that word I prime that have the maximum probability given if what I see is J star. And that becomes my kind of repair. If somebody already did the cleaning for the detection for you, chances are I do not need to know that devil and the pollution model. I just want to learn the parameters of this W, of the generative process, and I ask what will be the possible value of something that you don't trust if it came from the generative process. I'm going to skip this and come back to it later. So here is the conceptual model of Holoclean and how it follows this noisy channel model. All the red pieces here, all of these red cells, are identified as not trustworthy. Okay? So this is J star. The only difficulty, or the only thing that simplification here is, I already told you what the polluter did. I just want to recover the original value. I told you that Chicago is probably messed up by the polluter. What will be the most probable value that the intention model would have generated? and that becomes my repair. So all the black pieces are good pieces that I probably can learn that, that weight of the model directly. Now, nothing preventing you from learning these weights from everybody and say, you know, because I'm not sure if this is correct or not, but we're not going to get into that right now. So we're assuming that what we're learning from is clean data. So we're not going to learn from noisy or partial information. That's what I'm going to come to later. But what I'm getting here is clean observations with clean constraints, and I'm going to learn a model from this. So it's a lot simpler now. And I'm trying to make now this pass between learning from clean and unclean data. So I'm not sure if it's clean or not. Remember, if you want to do the end-to-end, I need to do two things. I need to know what the polluter did and what the intention model wanted to be. Yes? I simplified this problem. I already told you what the polluter did. So I don't now need to learn from noisy data. I just need to learn from the correct data what the intention model is. And I'm going to use the intention model to clean these things. One way is just to ignore these values completely, and I see if I can recover the value right away, for example. I treat it as a missing value imputation problem. So here is what I'm going to do. Every cell here, this cell, T1 city, this cell, T1 zip, this cell, T4 city, this cell, T4 zip, forget about these two for now, is a random variable. And we agreed we're going to use this factor graph model in which if I didn't tell you anything, these are completely independent. But when I tell you a constraint, I started to add structure that tell you how these things depend on each other. So the probability of any world become 1 over this partitioning function. But then I'm going to follow this exponential family where e to the power of some weight multiplying by the function of some factor that tell you how things depend on each other. Again, it's simpler. It's a lot simpler than it looks. This is just to normalize it. But the probability, if I'd like the probability of any set of records, any set of cells, all what I have to do is to apply the function of the constraint. This can be the number of violations, can be whatever it is, multiplied by the weight that you already learned. And that will give you the probability of seeing this thing. I just need to learn these weights. So we have two tasks right now to do repairing. Figure out these constraints, translate it into these functions, and learn their weights. Then I'm done. Then I did the two tasks of the challenges that I told you earlier. Remember two challenges we had earlier. How to put all the signals into one umbrella, which is figuring out these functions. And how to build a model that is capable of inference, which is figuring out these weights. So now becomes a thinking exercise and a database exercise, not a machine learning exercise. The first one, for example, is easy. Every city that co-occur, there is a factor that tells you, I'm going to prefer cities that co-occurred with this address over cities that did not co-occur with this address in the clean data. Make sense? Before this, every city here is equiprobable. T1.city can be anything. Chicago, Illinois, Lyon, Paris, it can be anything. So I looked and say, but there is an address here and this is clean. So I'm going to let me look in the rest of the data set. And if this address occurred with other cities, these cities probably will be more likely to appear here than a completely random city. It's unlikely that this is in Shanghai. Right? It's unlikely that this is even in Lyon. It's probably in something that has Morgan Street. Okay, so that becomes a factor. So the function here is if co-occurred, give it a brownie point. If it didn't co-occur, then give it the brownie point. So just by adding this factor, not all the cities, not all the zips are equiprobable anymore. Sounds good? So as if I went from a space and I dropped some magnets. around you, and now your values are a little bit pulled towards certain parts of the domain. Let's add another function that we are more familiar with. How do I translate a functional dependency in this? A functional dependency tells you, fine, you want to figure out the city and the zip and the city and the zip. Functional dependency tells you that you cannot figure out these things independently. Because if these things agree, these things should agree. Yes? Right? Fine. So in the possible worlds of the intention model, please prefer worlds in which when you agree on the zip, you also agree on the city, and give a slap on the hand of words that they agree on the zip, but they don't agree on the city. How much hard the slap is the weight, so you shouldn't worry about it. So the function tells you, if they agree with each other, you give it 1. If they don't agree, you give it -1. I'm going to multiply this by a penalty. This penalty can be as big as you want. In all the rule-based systems before, this penalty was max, was infinity. Right? We did not want any word that violate this constraint. Here I'm going to tell you I'm just going to learn it. Maybe it's not that hard of a constraint. So I did 2 things here for functional dependency. I turned it into a soft constraint, and I turned it into a learnable weight as well. So it becomes a factor. And I keep doing this. So you can see I now started to add structure in that domain. It went from completely unstructured domain like this, that looks like empty universe, to start things that are connected, where there are magnets that either connected to something that is constant or connected to some people to each other. So now would like to reuse this many, many times. You also notice that this is a template. This function dependency tells you zip determines city, yes? So any 4 combinations of 2 zips and 2 cities will have a factor like this. You can think of anything else. Like if you have a business rule that tell you the taxes cannot be more than the income, then there will be a factor between tax and income. So now all what you need to do is to take what guides the generative process and write these H functions and translate it as factors. And it will be nice. In the original HoloClean paper, we used a tool called Deep Dive because it allowed us to write these MLN-like programs that emits these templates. So I just say the template, and they generate that factor graph for me. After you're done, you have this massive graph with lots of connection between these random variables. What are the remaining tasks right now? We built the graph, so we have 2 things remaining. Learning and inference. I want to learn the weights, and then giving the weights, I would like to run inference to actually, and under general structure like this, actually inference is hard. It's as hard as SAT. Yes? Anyway, so there is a lot of results in harness learning and inference under general graph structures like this. We're not going to get into. So I'm going to go back now to just to show you even a small things that we do there as a side effect of thinking about this problem. So this is a paper that we had in UAI in 19, just talking about recovering these labels when the structure is even much simpler. So in the structure prediction part of the word, think about this is kind of an icing model where these are random variables, and the structure is limited to this type of thing. So it's not a general graph. It's everything is connected only to its neighbors. And assume that all of these things are Boolean random variables, and all the edges, all these factors, is a specific type of factor. We agree or we don't agree. Do we have the same label or we have different labels? And that's how far this is from the practical case of HoloClean, but these are the known results in structure prediction. Very, very simple case. And the latest results driving a lot of results on the Hamming error of what you can recover from these labels if there is noise in the labels and noise in the edges. So I tell you that they agree, but they actually shouldn't. And I tell you an observation that is wrong. So it's very close to us because we'd like to recover labels with noisy observations. And even this simple structure was hard. And we extended this where these random variables can be categorical attributes. And immediately in the Hamming error, you started to see, so this is the known, it was order Pn, order tilde, which is removing the log aspect. That's how much error you have, which is the noise in the data multiplied by actually the size of the data. So this is how the upper bound of how far can you be. Once you add categorical data, you started to be, the problem becomes more inflated by the size of the domain. So if you have a data set with large domain, and you just try to recover the errors, you need to worry about the size of the domain and how much noise is in the data. And that becomes upper bound on what you can recover. And we didn't even do it for different types of graphs. So let's go back to HoloClean. So here is how it kind of works. We assume that error detection has been already done. I'm going to come to that in a second. So data goes through error detection. The error detection might take the rules in, and it translate the data or classify the data into untrusted and trusted data. I'm going to use the trusted data, forget about domain pruning right now. And I'm going to compile all of this, the rules and the data, into big graphical, relaxed graphical model. And once I do this, I generate labels, I create that model, I run inference, and I give you suggested repairs. That is the goal. So let's see why this thing works. The first thing that we need to get rid of is this massive explosion because of the domain. Zip code can take tons of values. Cities can take tons of values. So in HoloClean, we do a bunch of domain pruning, so every random variable doesn't range over more than necessary. That was not as problem as tying weights. Remember in the picture that I showed you, every factor, every function has a weight with it, right? But it makes zero sense for us to learn a different weight for every instantiation of a factor. I want to learn one weight for all the for that template, for this function dependency template. So I need to tie these weights together so I don't learn different weights for every factor, for every instance, because you don't learn anything then. So I would like to see T1, T2, T1 city, T2 city, T1 zip, T2 zip will have a weight for their function dependency factor. That's exactly the same weight for T1 and T4. That's exactly the same weight for T4 and T5, because that weight is tied to the template of that factor graph, not to actual factor graph. Then you probably can learn something. And the most important thing that I think made the breakthrough in HoloClean was this constrained relaxation that I would like to spend some time on. Any questions so far? I think I tried to oversimplify things, so it might be a little bit hand-wavy, but the idea is to get the idea what are these things doing. Let's talk about what is the main problem and why the first instance of HoloClean, the baseline of HoloClean, took, I think, 30, 40 hours on a 1,000 machine for a small data set. And the reason is this. This factor that tells you when T1 zip equal T4 zip, make T1 city equal T4 city, it ranges over D to the 4 possible words, where D is the size of the domain. Can you appreciate this? Like when I sample from to see if you should take a brownie point or not, I'm sampling from the combination of all possible zip with all possible zip with all possible cities with all possible cities multiplied together. So that massive explosion in the grounding will never allow you to do inference, because the space that you're sampling from is D to the 4. So we're going to do something right now that will butcher this a little bit. It will get rid of it, but it will introduce new problems. So your challenge for the next 30 seconds is to tell me that I'm doing is wrong. So you need to find wrong stuff that we're doing. It's working, but you need to be bothered and annoyed with it. I'm going to do the following. I took this bad factor. This is a bad factor because it connected to 4 random variables. So we know that it ranges over D to the 4 possible words. And I'm going to generate 4 factors. Each one of those has to do with only one random variable by assuming the following. the factor that is connected to t1.zip, I'm sorry for the typo, this is t1.zip, actually tells you that when you choose t1.zip, make sure that it doesn't conflict with the current observation of t4zip and t4 city and t1 city. I.e., what will be the value of t1 zip if those were correct, the current observations were correct. So if t1 zip contradict with the current observation, give it a slap. If it doesn't contradict, give it a brownie point. And do the same for t1 city, t4 city, and t4 zip and t4 city. Now I have 4 factors instead of 1, but each one of those ranges over only the possible values. Yes? It becomes like a feature. I'm happy. Are you happy? Because I solved my problem. And I turned this constraint into this constraint. T1.zip should be equal 60608 if Chicago equals Chicago. Or, sorry, if T1.zip equals 60608, then Chicago is equal Chicago. This suggests that T1.zip should not be equal 60608. Because if it did, Chicago should be equal Chicago, and we know that Chicago is not Chicago. Okay. Same here. 60608 is equal 60608 means T1 city has to be equal Chicago. This suggests that T1 city should be Chicago. If you trust everybody else, the T1 city should be Chicago. If you trust everybody else, the T4 city should be Chicago. If you trust everything else, then T1 zip should not be 60608, and so on. That solves my inference problem. It becomes easier. Does it solve your problem? And I have time just for this, so I can wait for you as long as you want. This is important. I would like you to see if you appreciate this, because this is a big jump in between machine learning and why we're doing things. Are you not bothered by this? I mean, this is garbage. This tells you T1 city should be Chicago, and you guys know it's wrong. Yes? I mean, I did this because I said, okay, let me figure out T1 city, trusting everybody else. And I don't know which trust and which I don't trust, so I trusted the other one to make the inference for T1 city easy. But aren't you bothered by this? It's easier to inference because this factor graph is much more complex than this factor graph. Because now I went from the centered one that I have to this independent random variable business where each one of those has a feature, and their dependence is only through the observed instances. And for me, this looks like a logistic regression or like softmax, and I can do this with matrix multiplication. No problem. They are independent random variables, completely independent from each other. So I butchered the problem, and I'm happy, but you shouldn't be happy because this butchering of the problem will introduce errors. So what I've done right now is I took a problem in which I was seeking a global optimal to a problem in which I preferred local optimal near my current observations. Yes? At the expense of what? I mean, I might get here words that are still violating the constraint in general. Yes? Because I figured them independently from each other. So yes, butchering this and going to the local optimal might destroy things. However, I'm assuming that there are way more magnets than this magnet. And together, they're going to gravitate toward the right thing. So instead of seeking a global optimal that's trying to figure out the city and the city and the zip together and going through the domain, I'm asking everybody to look around them. Maybe we find something. So that is the new minimality. So we went from cardinality minimal repair to a more local optimal interpretation of minimality. I could have butchered this in a different way. I could turn this into, instead of from 4 to single random variable, I can turn this into 4 two-way. Yes? For example, see these two together and trust these two. Do these two together if these two are correct. I can do any relaxation I want. But, you know, so that's not the problem. The problem is if I go from a full model like this to a relaxed model, I soften the constraint even more. So the first layer in softening the constraint, I made it not a hard constraint, but a weighted constraint. And then I went and dissected into these small independent constraints based on the current observation, trying to say it's even relaxed, that I'm going to figure out each one of those independently. And these two tricks together should make two things. Implement minimality somehow by forcing this to not pick fresh values for all of these things together, but try to keep as many as possible from the observed ones. And it's a lot easier for inference and learning now. You guys see this? Again, relaxing Markov network is not new, but in this context it was. So we went from d to the 4 possible worlds to only 4D worlds where I interpreted this interpretation of the constraint. So the constraint now is completely butchered, as you can see. It's not even FD anymore, because it's, you know, that's not how you implement an FD. So putting things together, as I said, then we tie the weights by saying, you know, all the weights that talk about this FD conflict should be the same. All the weights that talk about the co-occurrence with another attribute like address should be the same. The co-occurrence with a different attribute should be also the same but different, and so on. So I reduce the number of weights, which makes it learnable, by learning the templates, not the instances. I cut the hard constraints into softer ones, and I cut the softer multi-random variable ones into even softer single random variable ones. And then I run inference, and it just works. Not all the time, because if you give this a very small data set with one constraint, you get garbage out, right? Because there is not enough redundancy to kind of outperform the butchering that you did for the constraint. Because if you have 20 and single FD, the best thing is to do a logical fix like we did before. But if you have a large number of data sets with a large number of instances of function dependency, then this gravitation will happen, and you will learn the weights of all of these features, and then you depend on the redundancy and the data that things will just go into the right direction. The actual implementation of HoloClean is not a PGM, of course, because there is no inference engine for PGM, and for other reasons. But I'm going to come back to this in a second. Let me show you. So this is the very original results of the very original HoloClean, and the result now is much better. And we, you know, hospital is a really embarrassing data set that nobody should use it, but we use it all the time because everybody's using it. It's a kind of injected typos in a 1,000 tuple. But there are other data sets as well. And we beat every HoloClean. The constraint only is the shoe stuff that I told you about before when we do minimum vertex cover. External only have very little coverage sometimes, but when it works, it works. Quantitative stats only is just co-occurrences. And we beat these kind of single tools. But here is what is more important. Forget about the x-axis. Let's take this with that. This is runtime. Forget about these three. Just focus on the first one. So no domain pruning. The blue one is the full model. Okay? And this is, and the orange one is the relaxed model when we butcher the constraint. The blue model, the full model, and the relaxed model. This is time, and this is accuracy. Are you surprised, or it's expected? So the full model is more expensive. We get that, right? But it's less accurate than the relaxed model. Benny, I want to, yeah, that's a question for you. What's your explanation to this?
No, but something interesting going on, because it seems like you're introducing independence in kind of in trade-off for performance. But it's not just performance, it's also
Minimality. course.
Now you have fewer rules with fewer grounding.
I'm not sure if I avoid overfitting. I think it's really more than we still overfit heavily for the observed data for everybody, but we are definitely pushing towards the close to the local observations more.
When you break the
Yes. Yes.
four variable rule into four rules, it's kind of you're saying, well, if you change to Chicago, you change to
Something else.
to a city,
It's okay.
well, they're independent. The choice of what
These choices are in there. Well, they are independent via the current observation. So there is this dependency that is hidden in the actual H function, right? So the dependence is now hidden in the feature itself, because the function, H function, used to tell you if these four variables are okay, then you give it a brownie point. Now the H function have instantiation in it. It tells you if it agrees with this particular zip and this, which is current observations of the other one. So I model dependence via the current observation, which is more pushing to the local solution. The problem is we're doing, or the reason we're doing more, is in this case, minimality was interpreted correctly. It was not cardinality minimal repair anymore. It's trying to tell people, keep as many good observations as you can. And the full model went ahead because, it was, under-specified. It went ahead and started to pick things from the domain that satisfied the constraint, but were very far away from the current observation. So it went ahead and changed the four cells together to make it conformant and get the brownie point. So it was overfitting to the constraint, while the other one was overfitting to the current observation. So it was an interesting phenomenon that you get. Of course, I mean, the right thing to do, if the full model was actually well specified and the structure was modeled a lot more and we have more training data, we're expecting this to be much better than that, because it will keep also the final instance with the constraint satisfied, which we are not guaranteed here. It's just with the same number of resources and the same number of training data, you never learn the correct full model, and it goes ahead and get kind of random assignments from the domain to satisfy it, while this guy had other constraints in it. So now the relaxed model came from a performance, but included a background knowledge in a very indirect way. So it was interesting. The current implementation of this is actually not PGMs at all. And I had questions from some of you before that lecture about, like, what do we do with embedding models and all that stuff, which is, it's a good question. Because, for example, it might be that one of the features, one of the factors can be the following. Let's assume that I'm fixing an address, okay? Or fixing a comment. I would like one of the factors to be, do I look correct or not? That's one of the factors. Not only what do I do with the rest, but if I fit this to an embedding model, do I look like an outlier or not? So nothing preventing you. So this is a diagram from Google, what the wide deep model. Think about that we have a bunch of what we call very sparse features. Co-occurrences, function dependencies, all of the things that I was talking about, including the actual representation of the actual record, that I can build a deeper model, for example, an embedding model or other kind of autoencoder-like thing to get more hidden layer features that model the correlation between these things, a little bit more complex than co-occurrences. For example, I can take all of these guys and I build a way to predict a context, for example, for it. As long as you are at the end, the output is taking this into account, and you have enough training data to learn that model, you're okay. So here's what we have done so far, just to keep you guys on track. We started by the noisy channel model. We figure out that the word is intention model and a pollution model, okay? And then we said, ignore the pollution model for now. I'm going to tell you where the errors are. Let's focus on the intention model. The intention model is nothing but this exponential family. Give me a word, I put the constraints, I figure out the violation, I know the weights, I give you the probability. Now let me put these constraints into context. We need to actually implement it. So we went into this factor graph business. Whatever you give me, I build a factor, conceptually. Implementation-wise, I have two options. Either I implement this using, I don't know, softmax, for example, or something like that. Or I keep enhancing these features to be a little bit more learnable factors. So, now because I'm treating this as independent things, then the implementation of this PGM can be as complex as you want. The only thing that I want to kind of convey to you that we didn't start by a deep neural network and put everything in it and say what a GAN will do for this. For example, when you're in trouble, you add more layers, and when you're in trouble, you add more layers. And if you're not sure, you try different dimension and k equal 100 and so on. There is nothing wrong with using a deep neural network here as long as you know what is it that you're implementing. It's approximating what. So the underlying layer are these kind of sparse features that are factors that you need to learn their weights. But the implementation can be a little bit more complex to take into account the representation layer of the input, for example, if there is a lot of text. For example, an autoencoder, this factor, remember this factor, address equal blah. I can get a factor that tell you, okay, I would like to prefer cities that are predictable by state and address and comment and salary and so on. How do I do this? I can build a layer or a neural network that take all of this into account and suggest a context for Chicago. And if you're closer to the context, you get a brownie point. If not, you don't get a brownie point in some lower dimension space. So the interpretation of a factor, all what I want to say, the interpretation of a factor function can be as complex as you want it to be. Like this. Okay? Ready for detection? You want to breathe a little bit, or you want to open this a little bit? Oh, you cannot. It's fine. Okay, so let's talk about the detection. So where did I cheat? Yes?
Maybe one question to Holocaine. So, where do you see it fail? For example, out of the main errors are probably problematic. What else would you say?
In this implementation?
Yes.
All the deep learning pitfalls are there. So out of vocabulary stuff, if you implement it bad, all of these can go bad. The other thing that I didn't tell you about Holoclean as well is the training data. I didn't tell you anything about the training data. So the training data we don't need any training data in Holoclean. We have the clean data, correct? So how do I manufacture, now I model this. To learn the weights of these things, I'm going to do exactly the same one, but I'm going to pick the city and the zip that are correct. Because we have other things that are correct, yes? So I'm going to pick the ones that are correct. And I know the right observation, because the right observation is a correct one. So in order to learn anything, I just have to manufacture examples of wrong ones. I know that the right city is Lyon. So I'm going to say, okay, if it's Chicago, I'm going to get these functions, and it's wrong. And if it's New York, it's wrong. And if it's Paris, it's wrong. And if it's Lyon, it's correct. So now I have positive and negative example that I manufactured in a weakly supervised way, in a self-supervised way. Once I'm done, I know the weights. I go and apply it to the don't know cells, and I just do inference there. I don't do learning. So it's two phases. I simulate if the correct ones were errors, how the feature will look like, and I know the correct observation, so I learn the weights, and I go and do the. That's kind of why it's a completely you just have to tell me what's wrong and what's not, and I learn it. Okay? Why I'm telling you this? Because in error detection, it's not the case at all. In error detection, I need to figure out the polluter, and I don't care about the intention model. I want to look at every cell, and I say, what is the probability that the polluter polluted that cell? Did it come from that distribution? Okay? Make sense? The main problem there is training data. Unlike repairing, there is no trustworthy data and non-trustworthy data that I can manufacture the correct data, the training data from to learn the model. I'm now in a chicken and egg problem. Without going through details, it's exactly like the repair model, where I have a lot of sparse features, character embedding, co-occurrence model, some tuple embedding, constraint violations, denial constraints, all the sparse features that were my factors in the repair. It's exactly the same. Okay? And I'm going to build a bunch, and I for every tuple, I featureize these tuples, and hopefully I just put it in this, as I said, deep, wide model to tell you at the end a classification task, which is the probability of something being an error or not. It's a simpler task from classification perspective because it's a Boolean classifier. In the repair, it was a multi-valued classifier. And in the case of numerical data, it was a regression. Yes? But here I just want to say, is it correct or not? What is the probability of correct, probability of not correct? So it's easy. I take the input and I feed it into this thing, and hopefully I can train that model. The biggest difficulty here is the training data. This model is as complex, but I cannot manufacture training data like before because it's a chicken and egg. There, I know what's correct, and I took the correct and I manufacture wrong ones. Yes? Here, I want to know if you're correct or not, so I don't know what to do. So the main insight there was, instead of building a model, this discriminative model that tell you if it's error or not, we actually built a devil model. And we learned that model first. So you show me very few examples of error, and you tell me we might have an error of a typo. This supposed to be that. This supposed to be this. There is an also transformation error. This supposed to be this. You give me examples of types of errors. And I say, thank you. I'm going to take this, and I build a model that sole purpose is to generate errors, not to find errors. So it goes and take these transformations and go to the whole data set and simulate assume it's correct, and simulate a wrong doing and generate an example of an error. And I featureize it as if it's an error. And this way you can manufacture as many errors as you want. So I take your data, your very few examples, I build a policy that generates error, I augment the data using this policy, I learned the complicated model using the examples of errors before. The problem now is you are as good as your model of the devil. Yes? If you model only typos, you're not going to discover but typos. If you didn't model anything, and so on. But it has much more modest training data requirement because I'm not learning this model directly. So the first module, for example, in the paper, there was this policy where it adds a character, it removes a character, it exchanges a character. You take me some examples of error, and I lift it up into some transformation. And then from these error examples, I learned the probability distribution of these actions. And then I applied it by, whenever you want training data, I apply it. I pick one at that probability, pick a clean cell, hit it with this pollution, add it to the training data, and keep manufacturing errors. Once you have this, I have a lot of now balanced set of training data for errors and non-errors. Yes? So I can now learn this difficult problem. The biggest problem in error detection was the imbalance problem. Very, very few errors, and any example that you pick at random is probably not an error. Once you have this, then the actual model training is trivial because it's that multi-layer thing that I told you, and the task is actually very, very easy, and then you're done. There are other, yes?
So I have one question. So you said like you learn these like transformations, like adding characters, removing, and so on. So like what about like for example field separation, where you have like a really like complicated arrow which have almost like no pattern. So if you give me like 5 different field separations,
I cannot, yeah.
so you might not be able to learn this double model.
Of course, fair enough. So this, as I said, I mean, this is a data augmentation way of doing data cleaning. It's or a few-shot learning. If I take few-shot learning in its general sense, there is assuming that there is a model that in this case you didn't learn, but it's a way to generate process that has all of these policies are equal probable, and from my examples I customize it to my case, right? So I'm using these few shots to learn that model. However, your assumption about that process is everything. So it generates certain types of errors, and if you're not modeling it, you're not gonna learn. For example, this doesn't model errors in numerical data, because numerical data is not removing a character. There is a definition of adding something and removing a decimal point. It doesn't model borrowing something from your next to you. Right. So all what I'm telling you here is you just have to be as complex as you want in this generative process. The only training data requirement is enough examples to learn the process, not to learn the discriminative model, which is much more hungrier for training data than this. It needs a balance and needs hundreds of thousands of examples, while the other one needs hundreds of examples, which is very, very different. There are other ways of doing this. I know that there are techniques for doing this pattern stuff. I know Shu in Georgia Tech, for example, they wanted to do training data generation by clustering on images. I know other people trying to find a way to extrapolate. So they ask the user, for example, on something, and they label. There was another paper in Sigmod in the same session as this. I think it's your Raha. This is Raha. Yeah. So and they do this. So they ask the user and say, okay, if the user said this is error, anything that look like it is an error. So people are after this. We really think that the few-shot learning, this data augmentation, is the most principled way of doing it because it allows you to focus on this generative model. But anyways, so this is the team that is building HoloClean. This is Shu, who was the mining constraints guy. And he's now, as I said, in Georgia Tech, and I think I managed to scare him completely, so he's not working on data cleaning anymore. He moved completely into, he's doing really exciting stuff on model selections, and he's still doing some cleaning in his style, but and we just finished the book together. George was much earlier student, and he did Tamer with me, and he's now still in Boston doing Tamer. He's one of the co-founders of Tamer. This George moved on, I think, to do something else, but these 4 are the HoloClean team, who Ali Reza did, he's more the theory guy. Benny knows him very well because he collaborates with his student on one of the pieces. And Josh and Omar are just starting in their 2nd year, and Mina graduating. And these are the collaborators that also I learned a lot from how to bridge this gap between machine learning and data cleaning. Mike, of course, I did Tamer with him. And Chris and Theo are the HoloClean original team, but Benny and Chris Desa helped a lot in really ironing out this noisy channel model. And this paper in ICDT, I didn't get into it, draws very nice connection when minimality of repair is exactly maximum likelihood estimation under the noisy channel model. And you'll understand why it doesn't work, because it aligns with under very heavy assumptions on the data of independence and so on. So now it makes sense. We understand why minimality, the way cardinality minimal repair doesn't work in general, because it is maximum likelihood estimation only if these assumptions work. While treating minimality as a guiding principle and using maximum likelihood estimation subsume thinking about minimality in this kind of narrow-sighted vision of it. So it should be encouraging you to think about many problems that we do under the hard constraint world and soft constraints, and think about it as inference. I think we have a lot to offer to the machine learning community, because we're coming from we're the constraints guys. We should, they hate MLNs and we love MLNs. Markov logic network vector graph and structure in the space. We're very good at this, and they are moving away from that. So I think we can contribute heavily to this to this environment. Does that make sense to all of you? I think I'm going to stop here. And I promised to stop early, and I lied. It was probabilistic statement, so it wasn't. And if you have any questions, I'm going to be around in these 2 days. The challenge that I was having for you is this open source Holoclean on the web. There is much more now than the actual paper, and it does regression on numerical data and what have you. But the idea was to see if any of you are interested in extending it with interesting stuff. For example, it doesn't currently work on multiple tables. What does it mean to have multiple tables there? And a particular one, I'm interested in the incremental aspect of Holoclean. Right now, it's take the data, build a model, impute, right? If I give you tomorrow, after you did this on 2 million records, then you're happy. If I give you 200, 300 records tomorrow, what can you do? So there is a lot of transfer learning, incremental maintenance of the model, incremental updating of the weights. Can you make it incremental end-to-end? So if you're interested in a challenge thinking about this problem, they are very clear challenges. How to make Holoclean an incremental version, for example, is an interesting challenge. I'd like to see if you guys have ideas, or even jump on it as a challenge download on GitHub and start to do a small POC with it to see if you can do it or not. If you're interested in different types of data, like for example, I didn't tell you what do we do with time series data. What the constraint on time series look like when I have temporal aspect into account. So it's not only on the innocence, but does something else. All of these are things around Holoclean that kind of start to extend its capabilities to different data types. I'm also more than happy to talk about these challenges with any of you. Well, thanks for listening, and I hope that was good. So,